And actually, David M. gave a very good overview of how old the field is and how much we are rediscovering and what is new. I teach a course in critical assessment of energy sustainability and climate, and I got somewhat worried about what often is taken as a fact about Halide perovskites when it seems to me that it's not really so. And so there should be lots of critique here from you if I give my opinion. And that explains the title. So I've been working in the Halide perovskites with Gary Holtz for 15 years or so. And there are several people that I have to thank, and they appear here from the Weizmann and elsewhere. And you will see sometimes some of them mentioned. But the responsibility is mine. I'm at an institute, fortunately, with lots of internal funding, and so with also some funding from an Israeli-Swedish program that has enabled this work. So are they really such amazing materials? And yes, I think so, but let's put things a little bit in perspective. So we are told in the introduction to many a paper that these materials have high this, high that, high such, and high so, including mobilities. They do not have high mobilities. They have nice mobilities, good enough for photovoltaics and also the other applications. And actually, just focusing on mobility, especially if you write a PV paper, as was mentioned yesterday by Christoph Brabeck, you should focus on the mu tau product and the alpha tau product, where alpha is the optical absorption coefficient. Then, often is written, one of the problems of these materials is that they are intrinsically unstable. And I argue they are not. They're intrinsically stable. What is unstable, which will not come to a surprise for many who remember Pauli's dictum about the bulk and the surface, is the surface and the interface for metal surfaces. Then we have defect tolerance. We heard about it already. It will appear in nearly every introduction. And what is tolerated? And what are those defects? When you enter into the thick of defects, you get to doping and dopants. And we have papers that have claimed that you can dope these materials this way and that way. And we'll look at one example, because I think in most cases there is no bulk doping. Finally, the materials are soft, that's correct. But we have scientific ways to actually figure out what soft means. Altogether, I do not question that one of the remarkable properties is resilience of the material over several timescales. Because the timescales are combined, you get remarkable effects. And this is directly related to their high optoelectronic quality, and I'll try to convince you of that. As such, I will not be surprised if there will be a future solid state and semiconductor physics textbook and solid state chemistry one that will have to have a chapter on this type of material. So the menu is given here, and I'll talk first about the self-healing and defect tolerance for this type of materials and how that is connected to the defects and doping. And then finally, try to figure out, put my finger on what is the real secret. We take several steps back and we want materials for energy conversion and storage. Then it's obvious that they will only do their function if they work if they are out of equilibrium. If they're far out of equilibrium, then we can get irreversible processes. And that's why, in my view, certain applications, like batteries, are more challenging than photovoltaics because you push the material way farther out of equilibrium. When you do that, you can get material degradation and breakdown, and then game over. Now, if you don't go too far, and you have a reversible process, then you can stop or limit the material degradation per se, and we call that, I would call that hard resistance, or by healing the damage or repairing. And slight semantic difference between healing and repairing is that self-repair is what happens when you have a wound, but you need extra material, which is in the system, and if none of that is needed, autonomous recovery, I would call self-healing. Now, the basic idea goes back a long time in semiconductors, in electronic materials. There's something called the silly detector. Some of you may know what it is. That is the lithium-drifted silicon radiation and particle detector that many of us experimentalists who work in solids will have used. For example, when you do EDS. It goes back to the 60s, and the way it's done is you take a piece of low-doped silicon, you drive lithium in, you drift it in by an electric field, and what happens is that the dominant dopant that's left in the low-doped silicon is boron. Lithium connects with essentially passivates the boron by combining with it in the silicon lattice. As such, you can get the doping density down by 3 orders of magnitude, making it a very good detector material, which still now is being used commercially. Now, what does this have to do with recovery? The lithium drifting is not always perfect, and you will have inhomogeneities in terms of the density of the lithium. That will immediately give rise to a change in potential and electric field, and that electric field is in the direction that will smoothen out your lithium profile. And that's how it works, otherwise it wouldn't work. That was not realized at the time, that came later, about 10, 15 years later. Another material that does remarkable things is also ran photovoltaic material, copper, indium, gallium selenide, because surprisingly, even though it seems very complicated, it has shown in real space tests that it is radiation resistant, at least as good as indium phosphide, which is a radiation hard material. And the reason is that the copper has a little bit of mobility. Enough so that it can influence the copper-related defects. Now, why would there be copper-related defects? Since the copper is the one that is mobile and the rest is not, or at least orders of magnitude less, means that those bonds of copper and selenium are the weakest ones, and that's where the damage will occur. Once they have occurred because of the mobility of the copper, which is naturally an absolute no-no in normal classical semiconductors, thermodynamics can do its work with the additional condition that the activation energy for such a process has to be moderate. If it's too high, then that won't work. Then the copper-related defects can move back, and you can also use happily the language for the secret language of point defects, the Kroger-Vig language, to explain what's happening. And this actually is, as far as I know, the beginning of the concept of defect tolerance, even though it was not called that way when Persson and Zunger, sometime in the late 90s, said copper indium selenide is such a good material because you can get complexes of defects which will neutralize each other, and that they didn't say, but we found, has to do with the mobility of the copper. So this is a material that is resilient, and it is so because of its dynamics not because of the static ability to withstand radiation. So it's a different type from what we have for radiation hardening. And that may be not unimportant in one of the challenges of today's electronics. So, and then came the Halide perovskites. And I show this picture often because for me research is standing in front of a brick wall and trying with my hand to find a loose stone, and suddenly there was this big hole I hadn't even tried. And now, naturally, people like David M. have been there a long time before. For me, the eureka came sometime in 2012. And for somebody who had been for a long time busy in optoelectronics, it was amazing. So yes, they behave beyond classical materials, no question. But I will pose that it all has to do with the dynamic lattice, and that somehow there has to be a connection between that lattice and the stability of the material, of the bulk material, stay away from the surface, and the high open circuit voltage. And that's what we're going to try to explain. First of all, the dynamic disorder is not just another material with dynamic disorder. It has with it amazing quality, high average order. And I do not know many materials that have that combination. In other words, that is why when we do diffraction experiments, and it was something that caught my attention when I first read about them, is the remarkable sharpness of the diffraction peaks. And that is explained because diffraction averages. And that means that things are moving, but they're moving around a very well-defined point, rather than with some blur. Now, the softness can be measured. Several years ago, both the Cambridge group of Cheetham and we measured the elastic constant. We also measured the hardness. And yes, in terms of the elastic constant and hardness, they are soft materials, but they're not that special. Because if you look at large families of materials, many lead salts have that behavior, not only the Halide perovskites. So, what's in between? Let's see. There are some assumptions that we often make when we try to describe solids, and some not only for solids, the harmonic approximation, widely used, or an Oppenheimer approximation, and they all are for these materials. And what is more important for this lecture is that when we dope a semiconductor, we make an assumption. And the organic semiconductor people should know this very well. But for the inorganic ones, it's taken for granted. And that is, once I put the dopant in there, it will stay put. Otherwise, it won't do the job. And that's why you get these, for me, rather bulky looking organic dopants, so that they will be sterically hindered and will stay in. Otherwise, they'll go out. Because those are also relatively dynamic materials. But they don't have that diffraction pattern. So they can self-heal. And that means that when defects form, they will be removed autonomously. And here's an example of an experiment we did with Aaron Baran, who was at the Weizmann then. Now he is in Berlin. And he did an AFM poking experiment, where you poke a hole in the pore surface of this crystal, and after 6 minutes in his AFM, it was gone. And here you see the line scans. In other words, this is something, by the way, that happens. I didn't know that. I learned it from him. In sodium chloride and potassium chloride, but at 750 degrees centigrade. And here it's room temperature. In this case, it was also in low vacuum. Then there is a beautiful experiment that was done by the Brown group of Patura, who took films of metal ammonium lead iodide, and they put them under stress, tensile stress. They managed to make a crack. Here's the crack. And then compressive stress or slight heating removed the crack. That's a nice picture. What actually is much more amazing is this one. It's X-ray diffraction. From X-ray diffraction, you can get strain, and from that to stress. And as some of you may know, this material in its equilibrium state has significant amount of stress. Now you crack it, and no surprise, the stress disappears, it's released. And then when it recovers, heals, the stress comes back. That's not something I've seen many materials do. We mostly study it by making photo damage and then detect photoluminescence. That's work of David Cerati now in Paris and with Gary Rakita now at Ben Gurion University. And so we did first 2-photon confocal microscopy, again, very much aware of Pauli's warning, so that we measured deep inside the crystal. That's where by 2-photon, by focusing the photons, we can get an upconversion so that the photon that is absorbed only is created in the center, and then you follow the luminescence. We also did 1-photon measurements, where we, at that point, had no encapsulation of the crystal. And so there are 3 stages before photo damage, what you see here in these grayish pictures, then the photo damage you'll see, and then the recovery. And you will notice that inside it recovers much faster than outside, and that is shown here also, because the surface itself will generally have some residual permanent damage. Because of loss of materials, the law of mass action, then you cannot heal anymore, or because of reactions. So we did this for metal ammonium, formaldinium, and cesium, in this case with very high light intensities, single crystals, and then later also for thin films, which then were covered with polyisobutylene, which turned out to be a good encapsulant. Because otherwise they would just not recover. What you see here is the difference between the 3 cations under extreme conditions. And the conclusion is that MAPI is the easiest damaged, it's most difficult to recover. Both cesium and formaldinium do that very well. And what I don't show here, because it's in a separate lecture, one of the main driving forces seems to be the strain. Built-in strain up to a point can help. Beyond that, it becomes a problem. And so the strain, it is not illogical because it will allow some nuclear motion, and for healing of damage, when bonds are broken, you need nuclear motion. We nowadays study not only the recovery as a function of time, but also as a function of space, and that is work that I've been doing for the last 3-4 years with Dan Oron, an optical physicist and microscopist. And the way that it works is, again, with encapsulated films, you damage 4 spots with increasing intensity, or 8 spots in this case. And then you look at what is the result, and as you can see here, the yellow is increased photoluminescence, the dark blue is the loss of photoluminescence. And that brightening occurs as fast as we can measure, in this case up till now only within 4 seconds. We're working on doing it faster, but already the 4 seconds is enough together with the distance to show that it cannot be an ionic effect. It's too fast. And then, therefore, we assign it to either energy or electronic carrier effects, most likely that traps that are being passivated temporarily because of the photogenerated carriers. And then the slower effect, which is the photo damage that we generally see, and more related to the general damage, is due to bond breaking. In a recent study that's not yet published, that we did together with the group of Iris Fischer at Ben Gurion University and Stable Care, we studied the single cation, double cation, triple cation, and this is the single cation. It's doing very poor. It's the metal ammonium, but with mixed halide in terms of healing, as you can see here for the line plots. Time on the x-axis and the photoluminescence on the y-axis. This is the dication and the trication, and as you can see, it gets better and better in terms of healing, although the higher intensity damaged spots, they do not completely heal. The next step was to go to complete photovoltaic cells. And there, we first added a whole transport layer. And you see, the healing is a lot better. This is all for the triple cation. The electron transport layer, also an improvement, not as good as for the HTL, and the complete cell. Again, it is a logical, there's a logical explanation. You get rid of these carriers that will do damage, and that may help in breaking bonds. Now, Michael can tell me if when you did that with Michael Saliba or Michael did it with you, that you had in mind all the time that this would heal better. I'm not sure, so it's likely an unintended consequence, but in science we often live off unintended consequences. Now, why can they heal so well? For that, we go back to thermodynamics, and many of you will have seen, or some of you may have seen it, fewer of you remember, that if you look at the thermodynamics of point effects, you add the first point effect, you gain a lot of free energy because of entropy, configurational entropy, and as you add more and more, that gain becomes smaller and smaller. So what you see here is that the free energy goes through a minimum. At that minimum, you have a thermodynamically dictated density of defects. That is something that every material, organized material, not amorphous, disorganized one, will have. The normal situation is that your free energy of formation or for decomposition is way higher than that for the defect formation. Because generally it's the enthalpy that's measured, that's what I give you. However, in halide perovskites, many groups, we among them, have measured the free energy that is needed for decomposition or for formation. And it's about 100 millielectron volts. If you add to that the activation energy, you get to something like 200 to 250 millielectron volts maximum. 200 is more reasonable. That's a very, very low energy for that reaction. That means that they can readily decompose and, as I already said, recompose. And now you have the opposite situation, because now the free energy of formation is way down there. I can get to work. Let's try this. No, but anyhow, it's here, and it's way down compared to the other. Yes, I should get that. So the energetics are upside down, and that is a thermodynamic explanation, which holds because of the low activation energy. Now, defect tolerance, I mentioned. It's a concept that has been used a lot. There's a beautiful paper, let's go back, by three theory groups of Egger, Rappe, and Kronig of 2019 that combined DFT with molecular dynamics, and they found a result that was then also found later by the group of Presdo, and I showed that picture, that the defect charge-discharge level in a perovskite, which you calculate with DFT, can fluctuate by an electron volt. Now, for a material with 1.5.1.7 electron volt gap, that's huge. And that, to me, was some strong theoretical support for, yes, if you have a defect that is within that range, then it will be discharged the moment it overlaps temporarily with one of the bands, if only because of an entropic driving force. There was no experimental evidence, and I admit that I set out to show that experimentally you can't find anything like that. And the result was the opposite. It happens sometimes. And so we found experimental evidence by comparing structural defects with optical effects, in this case, both surface photovoltaics, optoelectronic, and optical effects. But you cannot use it for everything, because there's here a simple Gedanken experiment. Take a material with a few defects. You damage it, you have more defects. You damage it, you have more defects. Now, if the defect tolerance was everything, then we would here be very happy with this material. However, if we take it ad extremis, at some point the material will have to give because there are too many defects. Therefore, that cannot be the ultimate reason. If you have self-healing, then at some point you will get back to your original state. Now, experimental data you find of both types. Often, the experiments are not done sufficiently controlled fashion to really draw strong conclusions. This is a detector material here, and this is a solar cell. But what is clear that if the solar cell is very carefully, or the detector, very carefully covered and protected from the ambient, that you get generally very little, if any, degradation of the effect. So what we conclude is that there are two effects. You create damage, you immediately get some defect tolerance kicking in until the self-healing, which requires movement of nuclei, sets in and takes over. And to be able to cover this time lag together with this, I think is a very special property of these materials. Thomas Kirchhardt, in discussions that I have often with him, and he was mentioned in Christoph's lecture yesterday, at one point he got a bit, I don't know, upset, annoyed, or fed up with my endless going on about defects, yes, defects, no. He said, I'll ask AI what the AI thinks about defects. And so credit goes to both him and AI for this blind elephant and the blind picture of a defect. Yeah, we'll come back to it. But we want to know what they are. Can they be? So for that, let's go to a nice organized lattice. And we have it here. And it's within a well-defined frame. There are some defects there. Now this is at 0K. If you look carefully, this is at room temperature, or a little bit above room temperature. Now we have to take into account that we have this material that wiggles and jiggles like crazy. Yes, admittedly around an equilibrium, but still. And we're going to put it in the straitjacket. So you'll get at best something like this, and I do not know anymore what's the defect here, what's not the defect. This illustration is meant to say that we have a model. The model assumes that we are on the left of this picture. What we are in reality is on the right of this picture. And that doesn't mean you can't use the model, but you have to be very careful with the outcomes. And so I can now try to use this and say, okay, I'll take the Schottky or Frankel defect model. It doesn't make much difference, and I calculate in terms of the energy for forming the defect, what will be the density of defects. It's a simple calculation. And Which energies? Well, we don't have isotope tracer studies for the Halide Perovskites, unfortunately, but we have them for lead iodide and lead bromide. And lead iodide is actually the more important one. To put things in perspective, it's a measurement of 95 years ago. But very good, because the Nobel Committee gave the Nobel Prize to one of the authors. So it must be right. Yeah. So if we do that, we see that we get here at about 10 to the 9. If you take the one of lead iodide, it will be 10 to the 10 per cubic centimeter defects. However, I can also argue that the decomposition and reformation free energy of the system is the determining energy. Because if anything above it, the system can get rid of it by decomposing and recomposing in a thought experiment. Yeah? So that we put here. And now we get to 10 to the 21. So my interpretation then is, okay, it's fine. This is the way that the fixed defect model copes with the dynamics of the system, and it gives me a 10 to the 21 per cubic centimeter number. That doesn't mean there are 10 to the 21 defects per cubic centimeter, but it does explain why in some publications it's written that we have very, very high defect concentrations, which I don't think is true. So we have made some progress here, and we have now the following in order to explain the connection with the stability, but we're still stuck with this high open circuit voltage. For that, look at the low experimental defect densities that have been measured for single crystals. It's 10 to the 10 per cubic centimeter. By the way, it's not easy to measure that. Several methods that are used are inapplicable. Again, I refer to Thomas, who has written about that in, I think, ACS Energy Letters. By the way, the 10 to the 50 per cubic centimeter is for cesium lead bromide that can be made both at room temperature and at high temperatures. And you see the difference. The polycrystalline films, they are also at pretty low densities. You can get them higher, but generally this is the range. And we are talking now about a number with 12 ninths. So how can this be? Let's look at a defect, a static defect. It will be a deep or steep electrostatic landscape, and dynamic defects, which will be a much shallower one. Let's add it to our picture, and now we have the low defect density, and therefore we can, by going from here to here, explain this high open circuit voltage. But how can we dope them at all? Well, we're back to this picture with all these questions. And whimsically, and for those of you who got the British education, you may understand it, we wrote sometimes back that the defects in Halide Perovskites can best be described if you consider the letters as a boojum. I don't have time to explain the boojum for those who haven't read Lewis Carroll. But we have to use Occam's razor, because the defects cannot be inside. They'll be kicked out. And any reports generally talk about anything from 2 to 10 atomic percent of the so-called dopant that is added. But they can be on the surface, and that is a known phenomenon with different names. And so you surface dope, and you get your carriers in the bulk. That is definitely possible. Now, there are several papers that claim bulk doping, and they're somewhat problematic. And I want to just point out one method that is a method I use. I'm not a great expert, but I work with a great expert, Antoine Cahen. And here we get a paper that gives us to the second decimal the ionization potential and the work function from this kind of plot, which is linear with this extrapolation. And it doesn't make sense. For example, I can be nasty and I'll say, okay, I'm going to do my own extrapolation. I actually get that the HOMO is above the Fermi level. So I won't go into the detail, but this is a problem, and we shouldn't do that. And this comes from papers published in highly reputable journals, and some of us review. We have to be careful because it goes in and it perpetuates itself. Okay, we got to this picture, and I got to the end. But I haven't explained to you how can it be dynamic. And the best explanation I have is that you have a bunch of atoms. They like to be together in a very nice ordered way, but they can't really find their one and only ideal position. And in the Halide perovskites, we have the octahedra moving with respect to each other, breathing, and we have the motion of the A cations. This means electrostatic charge averaging and dynamic dipoles. That seems to be the unifying factor for this kind of remarkable dynamics that they show. Some time back, these mysteries were posed to me by Thomas, and I think we have a problem with measuring defect densities because they're so low. But the chemical origin, I think, of these defects and recombination centers is at the surface, and at the long lifetime, it's because there's so few scatterers inside the bone. And about the last one, I have at the moment nothing intelligent to say. So the take-home messages are: the dynamic lattice is what imparts the self-healing and some tolerance to defects, and also the remarkable optoelectronic properties. And therefore, if we only can find now some smart way to make new materials that do that, it should be a big boon for high-quality materials and sustainable materials because they'll last longer. Thank you for your attention.
Questions?
Thanks, David, for a great talk. In one of your first slides, you mentioned this material, this type of material might deserve a chapter in the textbook. And then you mentioned several different properties. And if you can summarize, if we can, for example, maybe there in the future there will be more materials with similar features. And if you summarize this type of material is using one word or several combination of words, what word would you use for that?
My summary is that it would have to be a dynamic lattice where the dynamics do not prevent the exquisite average periodicity, because that is what I see here, and I do not know in all its way. But maybe somebody knows.
Thanks.
Okay, please, Anne-Marie.
There's also a question regarding the surface. So, talking, you were saying that the surface is the main, of course, issue of a source of disorder. Okay, but what do you think about also the way we grow the crystal? Okay, because what we found is that depending on the stoichiometry, we don't have. We should recognize that we don't have actual control of the stoichiometry during the crystal growing. But we saw that if this can happen, we are able to measure the diffraction pattern of the surface using lead. So you look at the first 1 nanometer, and you are able to measure the diffraction pattern of that. Does that mean that the surface can be actually order and not necessarily? Okay. So it's rather a matter of having control on how these crystals are grown rather than intrinsic.
No, I'm very glad that you asked it, because I realized I misled you. The surface is very good. If you do a scanning Kelvin probe and you are used to doing it on something like gallium arsenide that is not passivated, or copper indium selenide, you get an amplitude of 30 millivolts instead of 200 millivolts. That means it is. And part of the reason is, I think, that we did that only for the organic, inorganic ones, that you have an organic there, which is in full shell material. Yeah? Because on organics it's even better. So it's good. But if I start with a material that has 10 to the 11 per cubic centimeters carriers in the bulk, every that I do will give me an effect, even on such a good surface. Thank you for...
Okay, with this we thank David again.
Good morning, everyone. It's my great honor to be here. And thanks from and the committee members to allow me the opportunity. So today I'm going to persuade you. Okay. So today I'm going to persuade you that perovskite LED is a very promising thin film LED technologies, which shows high brightness with high efficiency. So we have already two very successful LED technologies. One is based on 3-5 semiconductors. As a lightning, I think it's everywhere. Also, the screen in front of us are made from 3-5 LEDs. It's assembling, I think it's more than 10 million LED chips together to have this display screens. And then if we want to have a mobile phone screens like this, then if you want to assembling over 100 millions, over 10 millions, that will be very difficult. So this is why thin film LED technology is important, as we talked yesterday. So it's very successful, has been used in mobile phones and in our monitor screens. So then, why we still need perovskite LEDs? So if we look at actually this data is from Carl Liu's paper. So if we look at the efficiency versus brightness for typical organic LEDs, and this shows very high efficiency at a relatively low brightness. Once the brightness goes higher, then the efficiency drops quickly. This is mainly due to two reasons. The first reason is because we need a much higher operation voltage at higher current density, since organic semiconductor has relatively low mobilities. And the second reason is since they're excitonic. So at high brightness, that means the exciton density goes to very high. Then excitonic quantum becomes inevitable. So which both factor kills the efficiency at high brightness. Then what's different with the perovskites? And we know it has a similar low temperature processing as organics, and it's a thin film technology, but their mobility is much higher than organic semiconductors. And secondly, they are less excitonic. The exciton bound energy is much lower than organic semiconductors. That means at a room temperature, it more or less like dielectric electron-hole combinations. So if you check this figure from Richard's publication, you will see typical three-dimensional perovskites. It maintain a very high PLQY even at very high excitations. So this tells us it could be a possible technology which can achieve high efficiency and high brightness, but still it's a thin film LEDs. So we started doing this field. We borrowed the idea from actually in organic communities. We use starting with a very simple device structure. It's ITO covered transparent electrodes, and then zinc oxide as a electron transporting and hole blocking layer, and then PEI as a interfacial modification layers, and then perovskite on top of it, and the TLB, which is conjugated polymer, has widely used in polymer LEDs as a hole transporting layer, and then molybdenum oxide and gold as a top electrodes. So with this simple device structure, if you check the performance, actually there's two features. It's very attractive. The first feature is you will see at a very low voltage, as low as 2 volts, you will see the current density always go to already goes to very high. It's about I think it's 100 milliampere per centimeter squares, and simultaneously we see the brightness increase quickly. And another feature is even more attractive is if you check the EQE versus current density, you see the EQE keeps growing at higher current densities, which is very different from organics. It's more or less close to 3-5 semiconductors. So this makes us a very polymorphism that looks like it really can make a high EQE LEDs with high brightness. But at that time, the EQE is still quite low. It's only about 3.5%. So we wanted to see if it's possible to make the peak EQE as high as nowadays organic LEDs, but at a much higher current density levels. So we know that the EQE is determined by these 3 factors: charge injection balance factor, and the relative recombination efficiency, and the light out coupling efficiency. Then if we check the films excitation dependent on the PLQE, and also the devices EQE dependent on excitation density, you will see actually these 2 curves are quite similar. They show high efficiency at high excitations, but low efficiency at the low excitations. So this is quite a good indication that it shows here actually the PLQE mainly is a very important limiting factors maybe. So we further confirm this by measuring the devices EL and PL simultaneously once the device is operation. And the idea is we wanted to see once the EL efficiencies increase or decrease, what happened with the PL. Actually, with this measurement, we found EL and PL, they are quite consistent. It's simultaneously increases and then simultaneously decreases. So this is a very good evidence, tells us in this low band gap perovskite emitters, the charge balance factor is near ideal. So the efficiency is mainly limited by the PL efficiency. So in the next few years, we mainly focus on how we can improve the PLQE and also the out-coupling efficiency. It's obvious that it's also very important. So for the photoluminescence efficiency, we know that's just David showed us about the layered perovskite a long time ago. Actually, in our case, actually, we found it's quite easy to make a so-called multiple quantum well structure, which is quite similar to 3-5 semiconductors. Just incorporate simultaneously the large organic cation with small organic cations together. And then spin coating, it will spontaneously form this structure. And then with this structure, you will see from optical measurements, you will see the different quantum wells absorption clearly. But the emission is mainly from low band gap ones. And then if you measure the PL excitation spectrum, they are more or less similar. So that tells us the existing kind of energy transfer between different band gap of quantum wells. And then we can measure this energy transfer process by ultra-fast spectroscopy. So it shows that at a very short time scale, for example, 0.5 picoseconds, this energy transfer already happened. In about 50 picoseconds time scales, this energy transfer is completed. So this is ultra-fast energy transfer process, which can concentrate all the kind of excited states, narrow down to the lower band gap perovskite domains, so can locally enhance their carrier density quickly. So with this, if you compare the 3D perovskites and the multiple quantum well perovskites PL characteristic, you will see even at a very low excitation intensity in the multiple quantum well case, it already shows quite high PLQE. So which is very different from 3D ones. That means the chip-assisted non-additive decay in this case is largely suppressed. So with this new perovskite layer, actually we can achieve then the device efficiency as high as 11.7%. So that means actually the internal quantum efficiency now is already about 50%. If you count the outer coupling efficiency, it's about 20%. So the energy conversion efficiency is about 8%. So if we want to further increase the device efficiency, one way we can do is with the further to improve it by enhancing the outer coupling efficiency. And for the perovskite case, there's another very different feature with the organic LEDs is the emitting layer. It's a crystalline materials. It's not like amorphous thin film organic emitting layers. So it's quite easy. We can form those kind of discrete structure if we control the concentration of the precursor solution well, and with kind of proper additive. Here is 5A VA1, which can passivate this crystal's surface, and then can easily form this kind of a scattering structure. And with this scattering structure, we can imagine the light can't be view guided inside the planar device, but can be largely scattering out to the outside. So we can calculate how much the outside for outer coupling efficiency can be enhanced. Actually, from the FDTD optical simulations, we found with the proper period of this discrete structure, outer coupling efficiency can be easily enhanced from 20% to 30%. So then with this well-passivated perovskite crystalline, the PLQY can be as high as 70%, and then with this kind of 30% of the outer coupling efficiency, now we can get a peak EQE about 20%. So this 20% of peak EQE actually is very close to nowadays mobile phones screens OLED efficiency. And we wanted to check, so what happened if we can further enhance the internal quantum efficiency by cooling down the device to low temperatures. At that case, we hope the trap-assisted non-reductive decay can be further suppressed by low temperature. Indeed, we can find actually the device efficiency, EL efficiency, is keep increasing at low temperatures. It can over 30% of EQEs. And in this case, actually, the EQE is already almost equals to the outer coupling efficiency. That means internal quantum efficiency now is at 100%. And the device shows actually is extremely stable at this temperature, since the ion migration is also suppressed. And we also measured their PL efficiency at various, as a function of temperature with various excitation intensities. You will see, indeed, when you lower down the temperature, the PL efficiency also keeps increasing. But interestingly is, at about 220 Kelvin case, the PL efficiency actually shows a abrupt enhancement in here, in this regime. And then we check the PL decay, challenge the PL decay, also shows the lifetime decreases with a lower temperature. But at a 220 Kelvin case, this kind of decreasing becomes suddenly becomes quicker. So then, what happened at this 220 Kelvin? If it's only suppressed with the trap-assisted non-reductive decay, then we wouldn't expect this kind of behavior with the temperature. So then we measure their absorption spectrum at different temperatures, and they're fitting their exciton banding energy of the perovskite. And actually we found this exciton banding energy at the 220 Kelvin case, it suddenly enhances from a few milli EV to about 15 milli EV. So this is something actually we unexpected. So later on, we checked with the Raman spectrum. We found actually there's existing a phase transition happened from alpha phase of Fe PBI3 to beta phase 1. So this happened at a room temperature. So we hope if it's possible, we can get the at a room temperature, then we can get the room temperature EL above 30%. So we tried many years to in order to find this kind of room temperature stable beta phase Fe PBI3 perovskites. Finally, we found it's possible by the with proper crystallization control, we can get the most of the beta phase of perovskites and with higher exciton binding energies. And with this higher exciton binding energy, if you compare their room temperature decay behavior, actually it shows speed up change in the PL decay with the ordinary one. And then if you check the initial PL intensity as a function of excitation intensity, so in this is a log scale. So if it's the bimolecular recombination case, a free electron hole recombination case, then you will expect a slope of 2. But in our case, actually in this case, the slope is 1.7. So that means it's not only bimolecular recombination, but it's a mixture of bimolecular recombination with the exciton recombination. Because if the exciton recombination, then the slope will be 1. So with this accelerated one, actually we can get the room temperature peak PLQE as high as 96%. And then the device EQE now goes up 32% of the device efficiency. So, with this, actually, we now believe the peak EQE now is almost equals to out-coupling efficiency at the room temperature. So then, how we can go further with the efficiency wise? So if we check the development of organic LEDs, actually go to tandem is a very important step, as yesterday introduced by speakers. So in OLED case, the idea is since the lifetime of the organic LEDs are dependent on the current density. So if you go to tandem case, you can use a half current density, you can get the same brightness. Okay. So you can get the combined EQE, and then so the operation lifetime can be greatly extended. And that's actually the tandem OLED actually nowadays is widely used in our mobile phone screens. If you want to apply same strategy in perovskite case, actually you will find it's very difficult, since this is a whole solution process, and the perovskite emission, the PL efficiency is very sensitive to the defect density, as I showed. So if you slightly damage the bottom perovskite layer, then the PL efficiency will be killed quickly. And so the tandem perovskite LED, if you check in literature, you will find you expect the 1 + 1 is equal to 2. Actually, the reality is 1 + 1 is smaller than 1. So in our case, actually, I have a very good PhD student, Cahen. He now is the postdoc in Feng's group. He found a very effective interconnection layer, which is consisted by moly oxide and H80 tin oxide and zinc oxide. We found with this combination of interconnection layer, you can quite well prevent the damage of the bottom perovskite layer when you deposition the top units. So with this well passivated one, actually the tandem efficiency we found it's even greater than the sumption of the two individual single units. So actually, the two single units here is about both of them about 20% of EQE, but the tandem one it goes to 45% of EQE, so which is unexpected, and that means now it's a 1 plus 1 is now it's greater than 2. So what happened? And then also if you check the lifetime, it's also it's a 1 plus 1 is greater than 2. And we can also tandem the different colors. Actually, one's in 740, another one is 800 nanometers. And then the tandem one, we can decoupling the emission spectrum, we can calculate the individual efficiency separately. And from this decoupling, we can still, we found single the tandem ones actually shows much higher efficiency than the single junction one. And then interestingly is the short wavelength ones actually slightly decrease the efficiency compared to single junction one. But the long wavelength one significantly increases the efficiency. Okay. So that tells us maybe the emission of the short wavelength was absorbed by the long wavelength unit, and then it will be re-emitted. But this kind of re-emitted, if it's a simple re-emission, then we would expect it will be no extra gain. It will be 1 plus 1 still equals to 2. But where is the extra gain comes from? We believe there's existing interlayer photon recycling happening in this case. So we check this by measuring the transient PR spectrum. So by use this kind of 740 and 800 nanometer emission layers stacked in this together, and then compare with this kind of two single individual layers. And then we're excited with 3 different excitation wavelengths. One is the blue one is can simultaneously excited the both layers, and then the yellow one only partially excited the short wavelengths, but can excite the long wavelengths. And then the brown one is only excited the long wavelengths, but no excitation with the short wavelengths. Okay. So then we check the change the PL lifetime. You will see actually the short wavelengths, they shows much longer lifetime compared to the long wavelengths in the single junction device. But if in the tandem case with the full excitation, you will see actually now the 800 nanometers emission now it's closer to the short wavelength emission. And this kind of increasement becomes less if you go to the partial excitation. Then this will then this kind of enhancement will disappear. It's almost consistent with the single layer if there's no excitation with the short wavelength. So that means the prolonged transient PR lifetime in the 800 nanometers in this tandem structure is due to excitation from a long-lived energy reservoir, which is from 740 nanometers. And so we can calculate, so how much the kind of energy transfer or the photon recycling happened within this stacked structure by this kind of dynamic equations. We can just easily put back a term which is emitted to this kind of reabsorption. By fitting this equation, actually, we can get the numbers about 18% of the energy transfer, interlayer energy transfer is happening here. So with this, we believe this kind of the extra gain from the interlayer photon recycling is due to because there's a kind of large emission angle light, which can be easily trapped inside the device as a waveguide mode. Then it now can be recycled by the perovskite layer and give another chance of emission. And with this, it can greatly enhance the outcoupling efficiency in this tandem structure and it gives 1 + 1 greater than 2 effects. And actually, we also did the optical simulation to see how much kind of gain can be obtained with this kind of extra, with kind of interlayer photorecycling effects. Our calculation shows it can be easily go to about 15% of out-coupled efficiency gain from this structure. So I give a summary here is I wish I have persuaded you actually perovskite LED is a good, it shows high efficiency and high brightness thin film LED technologies, and their peak EQE now it's almost equal to the out-coupling efficiency. And then in tandem case, a very high efficiency tandem device can be achieved even with 1 + 1 greater than 2. And with these effects, and the interlayer photorecycling plays very important roles. So since I have a few minutes, I would like to talk a little bit about the stability issues. So we did a little bit studies on the during the device degrading. So we want to see what happened. Actually, we checked the PL and the EL simultaneously once the device is degrading. We found that the EL degrading is much quicker than the PL. So that means the perovskite layer itself is degrading. It's not so fast. There's something else also happening. And we found actually this kind of degrading can be recovered if you apply a bias, apply a reverse bias. And then we put the device in a microscope, and then we observe their to observe their PL and the EL simultaneously. Actually, we just put the device in ambient environment, and then this dashed white line is the edge of the gold electrodes. So you can imagine the humidity and oxygen can easily come through to from this interface and then come inside the device. So you will see the black area can be easily developed from this interface. So this is the 0 minutes of the PL, and after 14 minutes, the PL, so it's the dark areas developed from the edge of electrodes. And interestingly, if you check the EL, the EL is this kind of dark area development much faster than the PL. So after 14 minutes, you will see this area is quite narrow, but if you compare the 12 minutes of the EL, it's much wider than the PL already. So that means this kind of degrading, it's before perovskite was degrading, something else has already happened. So this something else, we believe is the interface. So with this, actually, we know that in the kind of island structure or the scattering perovskite LEDs, we always put a kind of excess organic salt inside this emission layer. This kind of excess organic salt actually mainly stay between the kind of perovskite islands. So, and then this kind of organic salt can be easily has kind of mobile arms, or I think mainly here is highlights, which mobile highlights can attack the charge transport layer, can damage the LED quickly. So with this, actually, we found if we can treat the perovskite layer with the hydrophobic ligands, and then the top charge transport layer can be suspended. They have no chance to contact with the bottom kind of the iron source. And then with this structure, we found actually the perovskite LED can be very stable. So if you we measured at various constant current density case, you will see at 5 milliampere per centimeter square case, after 2000 of bias, almost no degrading. And if we compare this number with nowadays reported in literature different color or organic LEDs, actually we found this stability is already better than organic LEDs. So is anything beyond the LEDs? So I think people are very concerned about if it's possible to make electrically injection lasing with a perovskite. I believe it's a long dream in this community, since organic LED has a relatively low mobility. It's difficult to achieve. People hope since perovskite has a higher mobility, it could be easier. So we also tried this actually. We put our device, put a grating inside our device, and then we photo excited. And then actually we found that with this kind of grating integrated device, we can observe the CW lasing. And their threshold it seems not very high. It's 220 watt per centimeter squares. And then since this is a device, then it's a living device. So then we drive the device to see what happened with the pulsed mode. Actually, we found the device, the EQV, can live in very well. Even the current density goes to as high as 300 ampere per centimeter squares. So with this high current density, if you calculated it, you will find actually the carrier ejection rate has already exceeds the threshold of optical pumping. But still, we haven't found any lasing behavior yet. I think the device structure need to be more carefully designed to prevent kind of charge carrier leakage. Okay. So with this is my outlook. If we compare the three different LED technologies, we know the inorganic ones, they show very high efficiency, high EQEs at a current density is about 10 ampere per centimeter squares. That means it's looks like this screen they are very bright. But the problem is they can only make a small size. So we want to have the larger size thin film LED technologies. But organic one, usually they have peak EQEs, it's about few milliampere per centimeter squares. So now with the perovskite one, we can also make larger size, flexible, and thin film. We have peak EQEs about 100 milliampere per centimeter squares. So that means we can have at least the 2 orders of magnitude of more bright than the organic LEDs. Okay. So with this, I would like to thank my colleagues and collaborators across the world, and this is their findings. And this is my group in Nanjing, also work done by this brilliant person. Okay, thank you very much. And I have battery drawers available. And if you have WeChat, you can scan the WeChat code and also use emails. Thank you.
Questions? Please, Carl.
Thanks for the excellent talk. As you know, in organic LEDs, for the outcoupling, the orientation of the molecules plays an important role. You want to put them flat. Can you do something similar in perovskites with a 2D system or whatever?
Yes, actually, I think the people have tried this since the crystalline can be made very thin. So like 10 or 20 nanometers. In that case, people measured actually, indeed, they can manage the dipole orientation. It becomes more favorable.
Please, up there.
Thank you for a nice presentation. So on the next slide, do you know why for your LED, when you drive at higher current density, it's more stable than the low current density?
You mean the why is more stable at a low current density?
At high current density. Yeah.
At,
I mean at low current density.
Yes.
At reverse. Yeah.
Yes. Yeah, I mean, if you, I think there's a few reasons. I think if your current density goes too high, then your bias voltage also goes high. Then the ion migration it becomes, it's become faster with a larger electric field. And then another one I think it's excitation. It's a high density of excitation. Then it's more electrical chemical things can happen in the interface. Then so degrading fast at the high excitation. This is just my guess. So actually, similar thing in organic case. If you check the organic case, this is why we would like to have the tandem structure. Since a tandem you can have a lower current density, but you get the same brightness.
Thank you.
Since this figure is up, what is happening in this green line in early time when it's actually improving, kind of?
Yes, yes. This is so-called a positive aging. So, so positive aging. There's a few reasons. I think there's most possible thing is maybe something can do with the interface stuff. So if you bias with the electric field, you can get more favorable interface. So it can help us to inject the carrier easily. It might be. So I don't know yet.
Mine.
Yeah, thanks for your interesting talk. I'm here. I'm quite interested when you talk about the Perovskite multi-quantum wells. And you mentioned currently you use the solution method to make this kind of like very thin, I guess very thin, the quantum wells. How easy can you control the thickness with the spin coating, for example, compared to vapor method?
Yes. So the film thickness actually it can be easily controlled. But if you want to very fine control of every quantum wells thickness or structure, I think that will be tough. So it's a spin coating process. It's not epitaxial ones. So it's assembling of many different quantum wells together. So I show. Yeah. So it's just a kind of a lovely assembling.
Yeah, sure.
Yes, I was wondering what is the temperature of the perovskite when you drive it at the LEDs at different current densities?
Mm-hmm. Yes. So the temperature. I think the temperature is also a very important factor for the lifetime, since the higher temperature will accelerate the ion migrations. So in order to do this, actually, people have tried to maintain. Since now we did the device on top of glass. So if you did the device on top of like a silicon, for example, then or other substrates, we found actually the device the stability can be improved a lot. So in the measurement of the stability issues, actually, in order to have a good compare, so usually we keep the device in a constant temperature, for example, 20 degrees C, something like this.
There was a question up there. Yep, please.
Thank you for your presentation, first of all. About the degradations, if the degradations happens between the green boundary, I think the degradations should be uniformly happens inside of the device. But why there is a clear line between in the SEM or
Yes. So this line is because we deliberately do this. It's because we didn't encapsulate the device. We just put the device in air, and then later the oxygen and humidity comes through. Sorry. Yes. So this is because it's. This is why I believe the interface is also very important, because this is the dashed white line is the edge of the gold electrodes. So if the gold layer not covered, then you can imagine the oxygen and humidity can easily penetrate through the device, through the layers, and then the edge of the electrodes can be first. They are the first attacked. So this is why you will see it's developed from the edge.
Okay, with this, we thank Jianpu. And the next speaker is Tae-Woo Lee from Seoul National University, and this is again about light emitters, halide perovskite as next generation light emitters. Please.
Yeah. Oh, okay. Thank you for kind introduction. Also, I would like to use my mouse. What is this? I have red eye.
The first row.
Yes. Okay, so also I'd like to thank Gao and other organizers to have this kind of a good opportunity in this great symposium. Basically, I'm working on LED, also light emitting material for display. Today, I'm going to show some result related to this. Okay, this is content of my talk. So basically, in our lab, we are doing pretty much a wide range of the research, starting from synthesis of perovskite nanocrystals, also device fabrication. Also, we also collaborate with our company to make a real display, as shown in this figure. So we try to do recently make a 75-inch TV or 85-inch TV using Rotary process color conversion film, as shown here. And so when I was childhood or until 20 years ago, so we always used CRT TV. And then this moved to very thin LCD TV. And nowadays also using much thinner OLED TV display, also foldable phone. Also, so this kind of display innovation has been done, and then now we can ask what would be the next generation display platform. So basically, in our home, we are usually view the TV, but TV inside the home is just like content viewing devices. But we are moving toward new generation display beyond just simple content viewing display. So we are moving toward a certain display format which provide more immersive platform, which provide vivid color production and immersive experience and enhanced realism. To realize that, we need two essential technology. So first, we need REC 2020 compliant display technology. So for this, we actually need new types of material, like perovskite material, to provide vivid and true to color colors. Also, we need this kind of head-mount display or glasses for AR, VR display, which provide fully immersive and interactive user experience. So, so until now, I usually emphasize that the vivid display is pretty much important. Also, during the pandemic, so actually we watch TV all the time at house, in-house. And in this case, we need a very high color purity display. But until 2020, we have to meet two requirements. So UHD and this REC 2020. But UHD was realized, but this REC 2020 was not realized yet. So this perovskite is a very good candidate for realizing REC 2020 compliant colors. You see, so this on the right side, you see that so this is phosphorescent green. So for green, we still have this kind of red emission. So this has very broadened emission. So that's also iridium is very rare. So actually, eventually we have to replace this iridium complex-based material for display. QD is a little bit better, but still this is based on the quantum confinement effect. Therefore, spectrum can be broadened based on the ensemble of the nanoparticles. So perovskite is a very good candidate because this do not follow quantum confinement effect. This depends on the actually crystal itself, which provide various composition. This provides size independent, very narrow emission. Also, solution vacuum processing is possible. Color tuning is also very easy. So this is the history. OLED and QLED has been developed very long time. So you see, so always we had this kind of induction period, more than 10 years. And then the slope tends to change. And then steep progress has been done. So in OLED and QLED, but you see that starting from this Professor Richard Franz's publication in 2014, and 3 months later, our paper in 2014, November. And then, so skyrocket type of progress has been done. So this is very rapid. This is a kind of miracle in this display field. So now we are having 30% EQE without considering any outcoupling structure. This is pretty much on the par with conventional OLED and QLED technology. So you know, a number of propagation also has been increased since 2014. Also, we also published 2014 at the time. So brightness is around 400 nit, or the efficiency is 0.1%. So we are very excited to have this kind of devices with perovskite. But I have been grown in the OLED society. If I present my device and then they are not so interested in my talk, and then because the efficiency and brightness is so low, and then 1 year later we published a high efficiency perovskite LED, which actually belong to regime of phosphorescent OLED, because this exceed 5% EQE. After that, we try to make breakthrough in EQE. So actually, we started to apply our patent so in 2014, and we secured 8 different patent portfolio in 2014, including nanocrystal material and devices on processing, the application to LED and down conversion devices. Based on that, so we try to publish our paper one by one, starting from our advanced material and science paper. And recently, we published science and nature paper related to nanoparticle synthesis and color conversion application for display. So basically, you know, this perovskite emission is not new. So people tried a long time ago. Yeah, you see. So to 1994, light emission was tried, but this only possible at very low temperature, cryogenic temperature. So also very dim, so almost no emission at room temperature from the devices. So this has been kind of hard to solve problem in the perovskite field. And so this actually arises from the fundamental issue related to perovskite, so related to exciton binding energy and exciton diffusion length. So if we have a polycrystalline film, so we have a bulky grains, like 1 to 10 micrometer grain. So based on simple physics, so it is clear that we have to make a bigger grain with a small grain boundary, because grain boundary always has defective site, and this can deteriorate and quench the luminescence. Therefore, so conventional knowledge on the simple physics tells us that we have to make a bigger grain with a small grain boundary, but we cannot overcome the fundamental limitation related to the small exciton binding energy. So you know, at room temperature we have 26 millielectron volt energy, right? But the exciton binding energy is around 30 millielectron volt. very similar, right? So that's why the accidents easily dissociate into the charges. That's why this is more suitable for light harvesting, solar cells, rather than light emission. But I was pretty much fascinated with the colors of the perovskite material, and then I thought that if we make a display with this kind of very vivid colors, this is gonna be a next generation display material. And then I tried to think about counterintuitive approach strategy. So simple physics, in contrast to simple physics, we try to make a small grain with larger grain boundary. Yeah, then larger grain boundary is always a matter. But so with a special confinement of the charges into small dimension is the only way we can overcome this kind of a small action binding energy. That's why we try to make nanocrystalline perovskite, which consists of nanoscale polycrystalline material and quasi 2D material and nanoparticle, colloidal nanoparticle. Then we can effectively increase the action binding energy. And so this material is very special because this itself, by itself, meet RC 2020 color space. But you know, we need some kind of organic or hybrid perovskite material to meet RC 2020 compliant green colors. You see, session previously is actually debate from the pure RC 2020 colors, but if we have FA or MA, this actually meet RC 2020 pure green colors. So starting from our patent in 2014, actually we try to make a very clear strategy. So first we have to make a small grain or a small particle. And then we try to mimic the coarser nanoparticle in the polycrystalline film. Then we can make very high efficiency devices starting from 2015 science paper. And also we try to synthesize colloidal nanoparticle, and we try to make in situ core shell, also hierarchical core shell, and then this resulted in recent publication in Science this year. And also in our company, we are trying to make a 100-meter long roll-to-roll process film for display. And this year, our company was awarded CES Innovation Award due to this technology innovation in display. So this is a list of our patent. In 2014, we applied. Actually, it is quite difficult to get approval from the university to apply this 8 different patents at the same time. So I tried to persuade the university, and eventually we got this patent. And so this is already patented in globally. And so as I said, we need to have higher action binding energy. That's why we have to have a nanocrystalline perovskite, and then we can effectively increase action binding energy. So this is the critical direction in this LED field. So we need a special action confinement in small dimension. Also, we need to have an action buffer layer to block action catching at the interface. Also, we need to passivate any defect on the surface or interface, and especially in polycrystalline film. So we try to heal the defects at ground boundary using organic semiconductor such as TPBI or this kind of polar hydrogen bond material. Also, eventually we try to use BPA, which provide a covalent bond to the perovskite. And this is very effective to increase the efficiency and lifetime. Also, we started this structure actually. So we try to use bulky larger grain polycrystalline film at that time, but we try to avoid exciton catching at the interface, and then we can use this kind of exciton buffer layer, so which include PDA, PSS, perforated ionomer. Then this improve the efficiency, and then we can have light emission at room temperature. Also, efficiency is around 0.1, very low at the time. But we try to make a kind of a core shell like a polycrystalline film by mimicking core shell nanocrystal particles. Then how we make it, this kind of things. So most of the people are interested in how to make bigger grain. So actually at the time there was no process related to how to make a smaller grain. So that's why we try to make this kind of process called nanocrystal pinning process. So we applied non-volatile volatile solvent during the process. This is different from the anti-solvent dripping because we have to quickly quench the crystal growth, and then we can have smaller grain, but still we have to heal the grain boundary. That's why we have to need organic additive such as TPBI. This TPBI can effectively heal the grain defects. Then we can have 8.5% EQE. This is actually a kind of a sudden jump from the 0.8% EQE to the 8.5% EQE. And so more recently, we try to use new additive which provide covalent bond to the perovskite. That is benzyl phosphoric acid. This has a phosphoric acid group. So if we have a phosphoric acid group, this can make a covalent bond with uncoordinated PD2+. Also, we have a benzyl group. This actually mitigate a kind of insulating effect by the conjugated moiety. So this is very short. And if we incorporate this material into polycrystalline structure, this can be infiltrated into the defect site, and then this can be splitted into the small grain in like 10 to 12 or such a scale nanocrystals. And then this benzyl phosphoric acid, or so we are using many phosphoric acid material. So that was actually long time ago employed in OLED to make a self-assembled monolayer. So this phosphoric acid material is very good to make a very good self-assembly surrounding the nanocrystals by making a covalent bond with uncoordinated PB2+. And then we eventually had this 10 nanometer scale core shell structure. And then we can say that we had this kind of core shell structure using the covalent bond. But more importantly, I have to emphasize that we actually overcome the trade-off between the charge confinement and the charge transport. And so, we using this kind of approach, we didn't actually sacrifice charge transport, but we still have very good exciton confinement. That's why we can boost up efficiency and lifetime and brightness at the same time in this structure. So this is the result. So we had very high brightness. We had 10,000 nit at 2.7 volt. Also, we had 100,000 nit at 3.2 volts. So I was born in OLED society. In our lab, I cannot make such a bright device with OLED actually. So this is without incorporating state-of-the-art PIN technologies. So that is not actually accessible into the academia actually. So maybe so. This is also used 300 nanometer scale thick emitting material. So that's why this low voltage and high brightness is very remarkable. And So this will be eventually useful for future AR display applications. So we had this kind of record performance in 2022, and then so I'm going to share some result on the colloidal perovskite nanocrystal work. So based on our patent, we try to do research in this field, and then we try to make devices, large area fabrication on color conversion applications. And in this field, we need to think about so color purity, right? So if we stick to the quantum confinement regime, so we always undergoes spectral broadening. So we need to avoid this kind of quantum size regime. Also, perovskite nanocrystal has surface defect, also dynamic ligand binding, also dynamic disorder on the surface, nanoparticle surface, and therefore instability always a problem. So we need to overcome those problems. Also, scalability is very important for mass production. That's why we did our research step by step, starting from ambient synthesis and also side control using ligand beyond quantum size effect. Also, the guanidinium doping to passivate the bulk and the surface at the same time. Also, recently we did cold injection synthesis to make near unity PLQI. Even we synthesized at commercially viable scale, so like 20 liters. So conventionally, we are using hard injection. So if we use this hard injection for perovskite synthesis, so we have two or three main problems. So we need a high temperature, we need inert atmosphere. Also, if we like to have a monodispersed colloidal particle, we have to quench the reaction very quickly. Then, so there will be some kind of explosion or a problem of the batch reactor. So that's why we need to avoid this kind of problem. Then we have to have a low temperature process. Also, we need a more facile synthesis scheme. So also quality should be guaranteed as well. So also scalability also guaranteed. So we can do some kind of room temperature synthesis. We did starting from 2014, but this synthesis is actually very rapid at room temperature. So like reprecipitation method. So you see, so a very abrupt crystal is formed. Then this kind of low quality particles was generated. This doesn't look like cubic. And also we have to have the size, so beyond the quantum confinement regime. So otherwise we can have a broadened emission. That's why, so we try to have a little bit bigger nanocrystal beyond exton bore diameter. Also, we try to passivate defect with many different agents. First, we try to use guanidinium. This is very effective stabilized bulk. And then this can be enriched on the surface, and then defect can be fabricated at the surface as well. Also, when you fabricate the devices, you see, so we provide the shear to make a spin coating film, and then so suddenly this dynamic ligand can be detached, and then vacancy can be formed, and then we need additional defect fabricating agent on top of the film, and so we use the TB. And then finally, we can achieve a record efficiency at that time. Yeah, and we did large area printing. This nanocrystal is very good because we can decouple. the crystal growth with the film formation. Once a crystal is formed, we can do large area printing. This will be very useful for large area device fabrication. Recently, we did cold injection method. This is very useful to have a near unity efficiency at large scale, mass production scale synthesis. So, we have to use new scheme. So, LIFE use precipitate, but there is emergence as well. But immersion need a kind of demulsifier. But so we try to call our method is a kind of a pseudo immersion based cold injection method because we had a miscible solvent system. This should be transparent, but if we inject precursors, so it looks like milky, like an immersion. That's why we try to investigate what happens in the synthesis. You see here. So when we inject precursors into solvent, so within 100 millisecond, particle is formed, very rapid. So, but if we use this kind of pseudo immersion scheme, so if we inject the precursor solution, you see, particle is not formed until the same time scale. So this is very interesting. So that's why we try to investigate all the details. Then we found that if we how we can make this kind of pseudo immersion. So we have AX and BX2. So if we have very excessive AX pulses to BX2, this AX makes fully coordinated polyhalide probate. And then this AX can surround this probate. Then nucleation and growth can be controlled in a very well controlled manner. Also, if we cool down the temperature, ligand and PX2 interaction becomes much more strong. That's why nucleation growth is much more well controlled. And so this is our particle. So we can have very uniform and high quality crystals was formed. Also, productivity was significantly enhanced. Also, we do not have to use much DMF, so we can reduce DMF solution for eco-friendly synthesis. And at 20 liter scale, we still maintain near unity PLQI. And so light emitting diode also shows around 30%. This is close to the ideal EQE in this device structure. So recently we are focused on the color conversion application for real display. So QD OLED is very much commercialized recently. So we can replace this QD with Perovskite. So this Perovskite has a very high absorption coefficient. This is pretty much distinct from the conventional quantum dot. You see, we have almost 10 times higher absorption coefficient. That means we can have a much smaller pixel to make the same brightness. So that's why this is the only solution to make pixels less than 2 micrometer width and less than 2 micrometer thickness. That's why, so this is a very powerful technology for future AR/VR high density premium AR/VR display. And so to do that, we need to solve stability issues, efficiency issues, and so the thermal induced and photo-induced, so lattice expansion, soft the crystal lattice, softens crystal lattice. So that's why this lattice can be more vulnerable to the chemical reaction or degradation. Then we have to solve this kind of problem. Also, when we use color conversion pixels or something like that, they are concentrated. So we need to solve concentric catching, also photon recycling issues. And so that's why we try to have a hierarchical shell structure. In this structure, PbSO4 and SiO2 and polymer are actually interbonded to the lattice. And then, so this lattice breeding, is actually rocked by this hierarchical shell. And then this can be very stable. And so conventional benchmark for commercial display lifetime is here. So usually 1,000 hour with a 10% drop, but ours has almost 4 times longer lifetime. And also we compared with conventional cadmium technology. Cadmium technology also meet the commercial benchmark, but our efficiency is higher. Also, our lifetime is also very long. So, so when we use this kind of technology for color conversion, we need to define external quantum field, which is a product of the PLQI and the of substance. And so normally, if we have so 90% quantum dot, then so what happens? So self-absorption occur, and then photon cannot be recycled. But if we have near unity PLQI, even though we have self-absorption, photon can be recycled. That's why we can have very high EQI values among all kinds of the phosphors reported today. Also, this hierarchical shell showed no PV leakage in water more than 90 days. So we actually tested more than 1 year. No issues related to this. Also, we did a biological cell test, and then toxicity is almost same with the standard polystyrene film. And so we try to make a pattern. And so photo patterning is possible to realize the pixels above 3,000 ppi for AR/VR applications. Or also rotor processing is possible, and then we can make very long films, and then we can eventually make display. So starting from tablet to 75-inch TVs, and so in our company we can make films, and then we do this kind of lifetime study, and then we can compare conventional LCD and post-buy technology, and then you see that we can have a variety of display as shown in here. And this year, our company was awarded CS Innovation Award. Okay, let me summarize my talk. Yeah. Okay, so we started our work in 2014. And we try to overcome intrinsic problem related to exciton binding energy and exciton diffusion length in perovskite material. Then we try to have nanocrystalline perovskite, and then we try to apply this to LED and color conversion applications. And so basically, we try to solve low EL efficiency and low operational stability. Low EL efficiency is related to exciton binding energy. Low operation stability is related to ion migration usually. Also, we try to make a cost-effective synthesis method of perovskite nanocrystal. Also, we try to have a hierarchical coherent structure to overcome the stability issue for down conversion display application. In the future, we are expecting freeform factor display as well using perovskite technology. Also, AR/VR display technology will come soon. I hope. Yeah. Thank you very much for your kind attention. Yeah.
Thank you. Questions? Yes. Yes, Alan.
Congratulations, very impressive
Yeah.
progress.
Yeah, thank you very much.
And the question is, when we try to minimize the size, particle size to
Yeah.
pico size, okay? So,
Nano
is there
size.
any, say,
Yeah.
energy migration between particles,
Yeah.
the reabsorption of energy to the neighbor particle? Is it theoretically possible?
So you are talking about very small particle, like quantum dot size.
In contact.
Contact, yeah. So usually contact each other.
Mm.
Yeah. But we have a shell, multiple shell.
I know.
Yeah. Then this ionization can be mitigated. And
But
then
light can be reabsorbed by.
yeah. Light can be reabsorbed
Mm.
and then recycled like this. Step by step. Yeah.
Okay.
Yeah.
It's a very positive effect.
Yeah.
Okay.
Nam-Gyu.
Actually, the cold injection method is quite different from the hot injection method.
Yeah.
Usually, the compound semiconductor using some hot injection method to make the nanocrystal.
Yeah.
But your method is the cold injection.
Yeah.
So, is this method can be extended to some in general? Some compound semiconductor, not only the perovskite, salt type perovskite.
Yeah.
Kind of oxide. Or
Yeah. That's a very good question. So we didn't try yet. So basically, if pseudo emergent state is formed, cold injection can be tried. And then we didn't try it yet, but we tried all kinds of perovskite material. And then that works. And then extended to conventional QD or other material is kind of challenging. So we try to do in next step. Thank you for very good question. Yeah.
There was a question up there.
Professor Lee, we understand that in recent years you put in much efforts on commercializing quantum perovskite quantum dots for displaying.
Yeah.
The lesson what I learned from cadmium-based quantum dot is that for displaying is that using quantum dot as a down converting emissive layer is more commercially feasible combined with gallium nitride or fluorescent or organic OLED blue pixel. Compared to the case using quantum dot as a self-driven emissive layer, and also in your slide you have already highlighted you are going to go ahead with this approach that using perovskite quantum dot as a converting layer in your display device. So in this case, my question is, what would you think? Is it still important to go ahead with self-driven emissive perovskite quantum dot LED?
Yeah, very good question. Yeah, so but we do not call perovskite nanocrystal as perovskite quantum dot. Yeah, because usually the optimum nanoparticle size is exciton bore diameter. So usually 10 to 15 nanometer size is optimized usually. Also, even bigger size is better. And for PRQI and other lifetime. So that's why. So if you go to the quantum confinement regime, then we have a broadened emission like quantum dot. We lose our intrinsic advantage. That's why we have to avoid quantum confinement regime. Anyway, so if we use this kind of perovskite nanocrystal for self-emissive LED display, so we need a lot more time. Yeah, a lot more time. So you see the history of QLED, self-emissive LED, right? Then we need a lot more time. But so this color conversion technology is very powerful. So due to the self-absorption, strong self-absorption, so we can utilize this material from TV down to the very small AR/VR display. So this is very powerful. Conventional QD has very low absorption coefficient. That's why this material only useful for TV application or monitor, big monitor when you use our household electric power. So this cannot be used effectively to IT display, including all small display, even down to the AR, VR display. So that's why in QD field, we definitely need self-emissive QLED display. But so in perovskite nanocrystals, so we can collaborate with conventional micro OLED to make a VR display. We can collaborate with micro LED to make a very good AR display. So in the meantime, we do not need such a self-emissive display for the time being. But we eventually compete with micro LED to make AR display. So that's why its situation is a little bit different from the QLED history. But we are pretty much positive about the color conversion technology future, because this can be widely applicable to many applications for the time being. Yeah. Thank you very much for a very good question. Yeah.
Thank you. Yeah. Okay. Yeah. With this, it's a good point to give a good hand for the speaker and all the speakers.
Is Maksym from ETH, and he will talk about lead perovskites as a light source, quantum light source. Welcome.
Thank you. So, thank you for chairing and for the opportunity and honor to be here and to talk about the topic on quantum light sources using light perovskites. And just to give a credit to people which motivated our study in this direction are these historic works on lead inclusions in cesium bromide. Actually, they turned to be quantum dots, and that's already since 90s known, and specifically described as quantum dots in this paper. And when we go to colloidal work, we should give credit to our Greek colleagues who studied suspensions. These were not yet engineered as quantum dots, as nanocrystals. These were suspensions, but they were already attempts to generate highly emissive perovskite solution processable dispersions. And of course, very similar paper was also from Spain 2 years later. And so in our case, we were in particular motivated by this fully solid state work, and we set to make colloidal quantum dots in 2014, and that yielded us what we know as well-engineered colloidal quantum dots. That's where you have a discrete size dispersion, shape, and narrow dispersion of that shape as well. So uniform shape, uniform size. This was the work of my first doctoral student back then at ETH Zurich, and spectroscopy was taken care by Sergei. And as a young, and here it's a small story for our students. I learned there are 70% of students registered, and of course when we found that these are bright emitters as they are, you've seen these bright emission right in the colloid without the necessity for the epitaxial overcoating, we as chemists wanted to publish it in JACS. And JACS rejected it right away without review. And right away it says too specialized, unclear broader impact. And I agree with both statements, especially with the second one, because we are still discovering the broader impact of these materials. But we were very disappointed, and the students never be disappointed. If you've done something useful, something which others will repeat and use in their work and make it better, your work will still be well recognized. So in her case, the paper was cited 3 times a day, which is very good. I would be very happy as a student to publish a paper like that. So, and then we extended this to formamidinium based, and mixed halides, and so we could generate the entire basically rainbow of colors as a stable uniform quantum dots in the visible spectral range. This was super exciting, of course. And now a few words about why these are cuboids, because they expose 100-like facets, but we should remember that inside these are orthorhombic crystal structure. It comes important later. But they expose 6, that's why we call them cuboids, 100-like facets. And colloidal stabilization comes from replacing one of those ions, at least one, with a long chain ion, right, which has long aliphatic chain. So, and much later could we engineer highly monodispersed, very small quantum dots, because if you go down to just 3 nanometers here, it's 5 to 6 unit cells. For such soft matter, it's very difficult to generate them and to preserve them and use them eventually. So this is a credit to Quinton. And here what was also very important is that we were able to extend it also to methylammonium base, so to the entire family of hybrid ones. Even beyond those 3, as we were developing these chemistries in colloids, bulk research had discovered basically aziridinium as a cation. This was work of a different group, but we incorporated it as an A-side cation in the quantum dot. And just to give an idea, this ion, you cannot buy a salt of it. As soon as you try to make it, it will open up. But perovskite cage actually stabilizes it. And in return, this cation templates your perovskite formation. So it's a perfect synergy. And you see here the quantum dot of an impossible salt, because it's an impossible salt by normal means. And this even exists as a bright colloid. And just early last year, we published also monometal hydrazinium version of this. So basically, more or less, we are done with A-site exploration in this space. And as also Tae-Woo mentioned, there is a huge potential for down conversion displays. This is a Swiss company where you see the production at very low cost of 2 kilograms in one batch of formamidinium lead bromide quantum dots, these ones. And as briefly mentioned by Tae-Woo also, advantage of perovskites is way higher absorption coefficient. So with the same mass, you can produce 10 times more light, given high quantum efficiency, and also narrower emission line width. So very green color, right? And basically, in that arena of classical light sources, you now see that there are not only commercial, conventional quantum dot-based displays, but also perovskite nanocrystal-based products appear on the market. So this is in China last year. I'm sure in this year and next year, there will be many more products, presumably in Asia. And what is remarkable from scientific point of view, you have materials of very different sort of bonding type. One is highly covalent, like 3,5, and then a bit more ionic to 6, and then you have perovskites, which are very soft matter, very fragile. But if you make a composite in a polymer, it still will do that fantastic job in delivering light. And so basically, this was more or less a very short story of a decade of basically our own research in that arena. And now we will discuss light itself again. And so to give a full credit, the earliest paper, the earliest publication is this one, obviously, on the creation of light. But light sources actually were created a few chapters later. This was the sun, for example, and then just 150 years ago, Edison bulb, and 70 years ago, a laser. And these are classical light sources. If you look at the photon statistics, it's either super Poissonian or Poissonian. And in the last 10 to 20 years, there is a huge demand on quantum light sources, where you do control statistics of the emission per every pulse from your source. And the most fundamental here is single photon source. By far the most fundamental. It's a discrete, basically, stream of one photon at a time, without any fluctuation in the ideal case. And that's what we turn our attention now to. We're going to use perovskites as quantum light emitters, not as classical light emitters. And I will not overview all the known quantum light emitters. There is an excellent review by another group. I just want to point you that quantum light is the most missing resource in your future quantum applications of quantum light sources. Because for optical quantum computing, there are multi-billion investments into photonic quantum hardware, which will do all that work. But we have only a handful of single photon sources, and none of them satisfies all the conditions, all the requirements which we need. So we see that area as a huge opportunity for fundamental and for eventually applied research. So as a quantum dot, what you want it to be as a fast emitter. That's one big expectation. So quantum dot, actually definition of quantum dot is not only that there are quantum size effects. Actually, it's not a correct definition even. I would say it's a discrete electronic structure and tunable electronic structure. It does not need to be quantum confined necessarily. So a chunk of semiconductor acting as a two-level system is a quantum dot. And what you want it to be is a stream of very fast photons. And in a limit, if you have a sub-nanosecond radiative lifetime, purely theoretically, you can get 1 billion or more photons out of this quantum dot. Of course, you will be more limited with your laser repetition rate. And, but you want to have fast, saturable, and stable single photon emitter. Now, how do you look at a single quantum dot? That's where it's impossible to cheat in the publication. So basically, what you need to do, first of all, you need to isolate one dot. And what you do actually, you massively dilute your colloid, sometimes up to 100,000 times. So basically to this colorless, these are colorless dispersions. Actually, you need even sometimes even more dilute, some micrograms per milliliter. That's a homeopathic quantity of quantum dots. And imagine as you dilute it, even if you use very dry, air-free, moisture-free solvents, you multiply the residual ratio of those enemies of your quantum dot to your quantum dot by that same dilution factor. And then you start shining light on them. So it's eventually you want to pass currents through that and drive it even electrically, right? So this is the greatest torture you can expose your quantum dot to. Looking at just making the sample itself and then measuring that sample. So here, very important was a switch to these zwitterionic ligands. That's where we replace not only one ion at the surface, but two. So your ligand binds more firmly. And the best of these was the family based on these phospholipids. And so you do this massive dilution, and you hope your quantum dot will survive. And you know, these ligands, even if they attach a bit stronger, there is equilibrium. So as you dilute, you shift the equilibrium. So you are competing with all these problems, right? So just to give you an idea why stability was such a big issue. And then, if you are lucky, then it's a wide field microscope image. You put them microns apart. That's why you need that dilution level when you make a film. Then you look at a single one, and then hopefully you find these which are either non-blinking or almost non-blinking. In most cases, quantum dots, even those very usual ones, like cadmium-based and indium-based, they were photodegrading. Perovskites are defect tolerant, and they bring some advantages of that. Now, what you do, you actually, to study the photophysics most intrinsically, you put it in a cryostat, and so you disperse it after that dilution in a polymer film by spin coating, and then confocally you excite and collect the emission spectrum and the photon statistics from these two APDs. So basically the stream of emission from that single dot goes to this 50-50 beam splitter, and if it's a stream of one photon at a time, your photons will arrive on one fast detector or the other, but never at both. And so you look at the correlation between these two detectors and the time delay zero between them. There must be, ideally, this must go to zero, or at least be below 0.5 to formally qualify as a single photon source. And that was exciting discovery about 10 years ago, that these perovskite dots at low temperatures, when they feel more comfortable in vacuum, they are pretty stable, and they give us possibility to look at that intrinsic photophysics. And the third thing you want to look at is radiative lifetime. You remember this fast emission? You want to check if it's fast or not. And that is actually what you measure, this radiative lifetime. Moreover, by looking at single dot, you decouple, at low temperatures, you decouple all the inhomogeneous and homogeneous broadening effects. And so this was the next, or probably the biggest discovery back then, when we saw that they are very fast emitters. It's actually the only semiconductor quantum dot which at low temperature is a fast emitter. And the reason is simple. Usually quantum dots have this situation where the excitonic singlet state, which is dark state, is below the excitonic triplet state. And we talk about total angular momentum, not spin triplets, not like in lightweight organic molecules. Here, spin is not a good quantum number to describe the behavior. Here you talk about total angular momentum, and this state must be bright, but it's usually above. And so at low temperatures, you try to freeze all the problems, but at the same time, you push your relaxation through that dark state. Usually it's microseconds for most semiconductors, not with perovskites. And there is still debate why. There are two theories. One theory is that these states are probably inverted, for example, due to Rashba field, or the second theory, which is more likely, that there is some phonon bottleneck between these two states, and they're just not relaxing these carriers. They radiate from a higher line state. But the experimental result is that you have ultra-fast spontaneous emitter at low temperatures. This is first major discovery to be excited about back then. And the second, and these are collaborative works with Langbein in UK and with Bawendi at MIT, with very different techniques, could we see that these are also coherent emitters for most of the radiative lifetime. And in a limit, you want this emitter to be coherent basically the entire radiative lifetime, and then you are in a so-called Fourier transform limit. Only then you can do certain quantum optics experiments, which are absolutely fundamental for quantum applications, such as two-photon interference. If two full identical photons, and that comes only if they are coherent emitters, so that then each photon is the same, they will coalesce, they will exit this beam splitter together on one or the other side. This is a quantum optics logic operation, for example. So how do you get there, actually, with this to this equality, T2 and T1? You usually try to make radiative lifetime as short as possible, so as fast as possible emission. That's why it's so important to be fast. And optical coherence time as long as possible. Usually, quantum dots are not only slow at low temperatures, but also not very coherent. So some sub-picosecond or on the order of few picosecond the coherence times. Now, we don't know yet what drives this T2. We just know it's long enough, but you can shorten T1 potentially. So we will now discuss how we shorten T1 even further, how to make these emitters even faster and therefore even brighter and more quantum. So, and this goes to golden Fermi rule, where there are two important components. Local density of states, that's what people usually do. They put emitter in a cavity, and then there is a photonic density of states, and that enhances radiative rate of your emitter. The other is the material itself, but here you are not so flexible. It's either perovskite or something else. Except there are some special effects, and one of these is called giant oscillator strands, proposed by Immanuel Rashba, a major theoretical physicist in the former Soviet Union in Ukraine. He was the one who proposed that effect in Kyiv, and this soon it was verified to be possible in molecular systems, and now we see that 10 to 20 years ago, we see that in some of the epitaxial quantum dot materials and in perovskite quantum dots. So how do you see that? You tune the nanocrystal size to beyond the, well above the natural bore radius or bore diameter of your exciton. Here up to the factor of 5 or so above the bore diameter of the exciton. And normally you would get only problems by doing that. That's why people don't make quantum dots super large. But at low temperature, when we have all this coherence, we decouple your excitonic behavior, mostly decouple from the lattice vibrations. What we systematically observe that your quantum dot gets faster emitter as you make it larger, up to a point. Then some defects are accumulated, and statistically you lose that. But up to like factor of 5 to 6 of the bore diameter of the exciton, you get this effect. And that's beautiful because your emitter, your quantum dot, beyond in a very weak quantum confinement regime, when it gets into this basically superradiant state, this exciton coherently samples the entire oscillator strength from the entire volume. And your quantum dot is also more stable emitter because it's larger and it has a larger absorption cross-section. So all the benefits are there then because you reduce also surface to volume ratio and yet you preserve the ability to emit individual photons. So this was the big gift of nature in this case for these materials. And then of course you would ask, you should see it in the absorption because these are related processes. And indeed, even in a linear absorption spectrum, which is from an ensemble, not from a single dot, this gray curve, at room temperature looks quite featureless, mostly because of exciton-phonon coupling. And then you cool it down, and then so you sharpen your S, P, D, and other excitonic states. And you would expect that the ratios of those intensities, integrated intensities, should scale with degeneracy. But actually, S is much enhanced over P, and then the theory does say that indeed this giant oscillator strength will give you higher factor, higher enhancement of the absorption for S exciton over P exciton. And long story short, if you now plot these integrated absorbance enhancements and radiative rates, they scale more or less the same way. So this is these two sides of this giant oscillator strength effect. Now about problems. So far it looks like very exciting system, right? And there are of course problems and many problems. One is like that your triplet is actually, because of that orthorhombic lattice which we discussed before, is actually non-degenerate. It has three components, three orthogonal dipoles because of orthorhombic crystal structure. And so obviously if you look at the high resolution spectrum of that single dot, it's three lines. So it cannot be that these are indistinguishable photons. You either filter and it's difficult and you lose light, or you get rid of this degeneracy. In some epitaxial systems, they came up with some tricks by some fields and strain and everything, since we still need to learn how to do for this more scalable, more affordable quantum matter. But one trick which we just discovered is shape anisotropy. If you now take this cuboid, which is 6-facet bound nanocrystal, right, and extend it in one dimension, so that you achieve by making two facets grow faster than the other four during the formation. And above certain aspect ratio, you will see that you get only one emission line experimentally. Our current explanation is that emission dipole along this rod is put further apart of the other two and becomes a dominant, in this triplet manifold, dominant radiative channel. It occurs probably also because of giant oscillator strengths higher in that direction, and now you get down to 70 picosecond radiative time versus 250 for the same volume nanocrystal. You compare a cube of that volume and a rod of that volume. So this is at the moment the fastest emitter that we have as a spontaneous emitter. Now, coming back to this slide, you remember these zwitterions, right? These will turn to be the best ligands. And of these three, I mentioned the phosphocholine. This is a natural phospholipid. You eat it every day with chocolate, with soy products, with all this stuff. You consume a lot of this ligand. Not for this purpose, of course, but question is and we saw it's almost perfect. How we saw that? Because it worked very well for cesium, but not for hybrid perovskites. So there was something not yet perfectly set in that zwitterion. And then we examined it closer, these zwitterions, these phospholipids. So again, this is phosphocholine. This is this trimethyl ammonium, quaternary ammonium zwitterion. But there are also these primary ammonium. Some of them are also physiological natural, and many more we have synthesized. And we could vary we produced by now probably 100 of these, which vary in the lengths here, of this lengths and type of this chain, as well as the splitting between the ammonium and phosphate moieties. And in silico, so in the classical molecular dynamic simulation, under supervision of Andrei Baumgartner, our good friend from Ukraine, theoretical chemist, and these three students mainly drove this project. They synthesize these molecules to prove that indeed, when you go to a more compact primary ammonium moiety, it better fits instead of cesium or formamidinium on the surface. And then, in relation to which halide you have, chloride, bromide, iodide, you also vary these lengths, this basically, and then you can lattice match A and X site on the surface so that you replace them with the head group of your zwitterion. And that, you remember now, the initial problem was this dilution, right? Ligands tend to desorb. This is schematically sketched here, and if they desorb fully, nanocrystals are destroyed. So now this little change for the synthetic organic chemistry from quaternary to primary ammonium turned to be a giant leap for the spectroscopist experience, basically, because you see here that you're statistically also, not some champion dots, but statistically, your dots have become much more stable. And you see that from intensity retention and from emission line energy retention, because when the dot photodegrades upon measurement, it gets smaller, it gets bluer because of quantum size effects, and then fades away, so the intensity disappears. And now, from this very good ligand to this much better ligand, this was a huge jump in the experience, and that was now for hybrid ones. So we finally could study hybrid perovskites, not only fully inorganic one, but the hybrid ones as single dot entities, and they have become stable for hours, and that's beautiful, and at room temperature. So not low temperature and vacuum, but room temperature, more like ambient conditions, and mostly in the on state. And now it's even better. This was a few years back. And so Leon Feld, the student who started to systematically look at this single photon purity in relation to whether you use fully inorganic or more soft hybrid perovskite. And what he saw, that again, against all the usual rules, the single photon purity from hybrid dots at room temperature was size independent. Why it should be size dependent to start with, right? Let me explain you briefly. Normally, single photon purity is compromised by the larger contribution from biexcitons, and at room temperature you cannot separate that. It's all one band. And so, actually, your single photon purity is a measure of this biexcitonic contribution. Normally, quantum dots are downsized to enhance so-called Auger-Meitner recombination. Actually, here I also would like to point, in the context of our historic tour yesterday, Lise Meitner, whom we owe a lot of historic debt, is also here because she actually discovered this process, which was termed Auger process. And she discovered it also in the context of her nuclear fission experiments. And so we recommend calling it Auger-Meitner recombination. And that is a process where basically one electron-hole pair will give energy non-radiatively, will be, so exciton decays non-radiatively to an exciton, and then exciton decays radiatively. And so this Auger-Meitner recombination process actually is the one which purifies your system out of biexcitons, but the only way to enhance it was downsizing, and that's deadly, because very small dots are very unstable. But somehow this is not needed in our case of hybrid perovskites. And so Leon, who is not only a good experimental, but also very good computational scientist, he just defended his PhD a few months ago, he came up with the simulation, initially hypothesis and simulation, that because of the structure dynamics, because of the softness of these perovskites, which was discussed a lot, there is additional confinement potential which breaks basically coherence lengths of your wave function of your electrons and holes. So that enhances, without physically downsizing the quantum dot, that process enhances this decay of biexcitons. And so these are his ab initio molecular dynamics DFT simulations, comparing slightly more rigid cesium and more soft hybrid perovskite. Indeed, much more localization as you warm up the quantum dot to room temperature. And that's not static localization, it still, the exciton generally sees the entire nanocrystal. And you get now at quite large sizes, stable single photon emitter at room temperature, such that you can basically saturate it. And this brings us to one major advantage. And because of that softness, that it is softness driven, it applies also to all the other hybrid ones, including the impossible salt of aziridinium. It's also a very good room temperature single photon emitter. And now why it's important? Because you start potentially, you may finally start harnessing quantum advantages of having quantum dots at all. Not just to have them as classical fluorescent emitter, but actually to have them as quantum emitter. Look at the laser. If you try to make single photon source out of laser by attenuation, you will not make it because it's still gonna be a shot noise limited source. Still, your shot noise will be limited by basically signal to noise ratio will be square root of the mean photon flux per pulse. And no matter what you do, you will always have shot noise. Now, if you go to single photon sources, as we did, we first, and then there are applications, of course, I will not discuss them much, but it was important not only to go to single dot photon sources, but to actually get that stability, because all the off times are also contributing to your effective fluctuations. But if you have a single photon source, stable and pure, you eventually will go to zero. You will not have noise. You can imagine optical microscopy at much lower intensities, for example, plus quantum correlations for super resolution and things like that. So, and then you will start getting less of that intrinsic shot noise in your emission. So that's basically what Leon also had seen first signatures with these new ligands, with these, because of this localization in this formamidinium system, he started to analyze actually the noise that he records from single dot at room temperature. And he sees that already in the measured flux, he sees lower standard deviation in the photon flux than there must be for that mean value. And then if you also take into account that he loses 70% of photons in that specific setup, that probably gives you a number of close to 50% intensity squeezed quantum light generation from this. All right, so just a quick summary. Comparing to conventional Poissonian and super Poissonian light sources, with quantum dots, we first, a decade ago, could see that they are relatively clean single photon emitters. Then we improved single photon purity and the rate, and eventually the stability. So these are all good news at a single photon emission. Now a bit of outlook, just 2 minutes. One is that you've seen everything so far in green. Red is a bit more interesting. All the optical fibers, detectors, background fluorescence are all much better in the near infrared, 800 to 900 nanometers. You need to go to thin systems, which were discussed before. Making quantum dots out of them is even more painful in terms of stability and all these did open, but we do have some unpublished good progress here. We get relatively bright emitters which are thin or lead thin based, going even beyond 1000 nanometers in the emission from a quantum dot based on thin. And then another outlook is, what if you go not to single photon sources, but discrete and photon sources? Many of these quantum benefits will be further magnified, and other chances there. And the very last slide will be this one. This is very old data from us. Again, collaboration with these wonderful scientists back then at IBM. One of them is our group member, Gabriele Raino, Marina from Empa. Thilo is still at IBM. So we work over these years studying the superfluorescence. Initially observed quite unexpectedly, actually, by cooling down the film of these dots. Then we realized that that comes from order. And then we made superlattices deliberately, these giant superlattices, and these were yielding us reproducibly this collective emission, which is much accelerated emission due to coupling of these coherent emitters to build coherence in a larger sub-wavelength volume of the light. And so then we started to engineer that property through the structure. And the future outlook is that we still cannot control how many of these dots are there coupling. So the future is here to get discrete photon source, you have to have discrete quantum dot aggregate of coupled dots. That's something maybe to do for the next 10 years or so. Thank you.
Thank you very much, Maksym, also for leaving good time for questions from the audience. Toin, please.
Thank you, Maksym. Very nice indeed. So you presented 2 ways to get, let's say, gigantic dipole moment. One to make the large quantum dots.
And the other to couple.
But then you put them together, you get it even larger. So what do you think? Which way will...
We need both.
Say it again.
We need both, because the first one will still give you single photon stream.
Yeah.
It's just a larger coherence from the same 2-level system. Whereas the second one delivers you bursts of, in this case, the spontaneously formed domains during superfluorescent emission are 20 to 30. If we calculate from the amount of acceleration of emission, it's tens of dots coupling together. So if your goal is discrete, multiphotonic, hope maybe entangled, whatever, sources, you need to make individual dots well-behaved, coherent, and then put them together somehow that they know each other. Yeah.
Thank you.
Thank you.
Yeah, thank you for a nice work. I have a general questions about the single photon emissions. So I'm questions about will the size of the quantum dots affect this property? For example, for 5 nanometer quantum dots or 1 nanometer quantum dots, yes, and any difference?
So, in relation to size for perovskite dots, if you go very small, you have at room temperature, for example. You have very clean single photon emission. You get acceleration also because of quantum confinement. You increase band gap. Golden Fermi rule tells you it will be faster emission. So you do get these 2 benefits. You compromise a lot on stability. Surface to volume ratio is huge. All the instabilities are magnified, such that hybrid perovskite dots like sub 5 nanometers, even with best ligands, even with some Schelling tricks which we also have, we cannot stabilize it.
Okay.
Now, if you go to medium confinement, you sort of, if you go to the other extreme, like very large dots, you start getting contributions from multi-excitons a bit higher, but your exciton itself, so biexciton, triexciton, start to appear in your spectra much more prominently. But you get the following. You get overall a bit more rigid entity, so the coherence time is a bit faster. Coherence time is longer, radiative rate is faster. So for this, where you do need to have coherence, you need to make them large, I believe, but not too large.
Okay.
Yeah.
Thank you. Yeah.
Okay, one last question.
Thank you very much for the insightful material design and the understanding of physics in this kind of quantum side. I have also a very general question about some kind of future. Like currently, with some kind of quantum communication application already being developed and applied in some kind of test environment. And I think currently what you have in your lab is some kind of material on the glass or some kind of substrate. So what do you think about the future? Like what kind of form it will be in the future applications?
So you mentioned quantum communication, very good one. Because all these demonstrators, which we've seen also from China, even Earth to satellite,
Yes.
all are obtained with attenuated lasers.
Yes.
So it's conceptually correct, but it's unusable. It's very low, basically, or with the parametric down-converted generation of entangled photons, for example. So it's very good science, but it's not, so these dots offer you that scalability, the rate, potentially all of that. So I think on a short term, and short term here is maybe 5 to 10 years, this quantum communication will be demonstrated with perovskite quantum dots, and possibly some of the quantum imaging ideas. There are several ways to use quantum dots, either as light source or as labels, to increase the spatial resolution without using massively intensive lasers or whatever. So these two directions, I believe, or we believe as a team, I would say, because we are trying to pursue them eventually. Yeah.
Yeah, I also like to thank Maksym for sharing your publication experience.
Okay, so thanks a lot for the kind invitation. Let's see if this now works in my case. It's not working. Okay, so I don't need to make an introduction on quantum dots because the others have already said a lot. I just want to say that in this material it's very easy to change the color of emission, for example, by changing the halide composition, and the synthesis it's also very easy. This is an historical, let's say, timeline of perovskite. They were known since a long time, but of course only in the 60s people started realizing that hollow plumbates have the perovskite structure, and then we have the developments that Maksym has shown in his presentation. Now, the issue with perovskite, as Maksym has pointed out, is surface is very labile, so ligands easily come off, and so we need to find better ligands to passivate the surface, like zwitter ions, or maybe even ions that just have a stable positive or negative charge. For example, quaternary ammonium ions, which we have developed last years. So, for example, you can start from a sample of cesium-08 cap nanocrystal, which are highly unstable, and easily replace them with their surface with quaternary ammonium ions, which have a stable positive charge. And these nanocrystals remain stable over weeks, contrary to the starting nanocrystals. Now, you can actually play a lot with this quaternary ammonium cap nanocrystal, and we found out that, for example, if you treat them with the phosphonic acids, you can remove up to 40% of the ligands on the surface of these nanocrystals. yet the PL quantum yield remains high, which points to some kind of surface stability, surface tolerance of this material. So we said, okay, lower density of ligands means maybe better transport in films. Okay, so when you move to actually from solution to films, of course, the PL quantum yield goes down with the extensive treatment with the bisphosphonic acid, which strips the ligands. And there you see that the effects really start kicking in, and you cannot really fight against them. So there is a trade-off, for example, when you remove just a small amount of ligands from the surface of nanocrystals, where the PL quantum yield goes down a little bit, but you increase the mobility, and this turns out to be, leading to devices with a higher external quantum efficiency than sample in which this treatment is not done and it's just washed with a simple solvent to remove excess free ligands from the solution. Now, there are many ligands that you can use to passivate the surface of the crystal. So, for example, what we recently did was to use quaternary phosphonium ligands, which are actually also stable in organic solvents. And they're a bit skinnier, for example, than the quaternary ammonium ligands that we usually use in the synthesis, in the passivation of nanocrystals. And so we did a lot of studies to make sure that these ligands really passivate nicely the surface of the nanocrystals, and they lead to nanocrystals that are stable over weeks or even months. They never degrade. And because the density of alkyl ligands now on the surface is kind of low, if they're used actually in devices, they turn out to beat the comparative devices made with quaternary ammonium halide ligand pairs. Okay, so just to give you an idea of the surface chemistry that groups like us or Maksym are exploiting, and other groups that you have seen before to make this nanocrystal stable. We're not a group that aims to make devices with very high efficiency, because we are not really equipped for that. We use devices basically as a benchmark to see the effectiveness of our ligand treatment. Of course, if you want to make very stable nanocrystals, you have to grow them into some sort of hard templates. So this is a method we developed years ago to grow them into mesoporous silica in molten salts, which basically end up sealing completely the nanocrystals into the silica pores and completely collapsing the outer pores, so that the nanocrystals remain completely isolated from the external environment. And you can easily even throw them in aqua regia, okay, and they remain stable for a week, okay. So an evolution of that work was, okay, growing them into smaller beads of mesoporous silica with the same approach, so that the final suspension is not so scattering light as in the previous case. Again, high stability in aqua regia, and now these materials were used as the green down converting layer in prototype display that we developed in collaboration with Quantum Solution. I feel ashamed of showing these results after the beautiful talk before lunch, where extremely high efficiency and wide area devices were shown. But again, we are not a group targeting this kind of application. We're mainly looking at surface chemistry or developing new colloidal synthesis routes in general. So one thing we notice about this synthesis of perovskite nanocrystal is that to get high monodispersed nanocrystals, you have to use a lot of lead, an excess of lead. So the yield in terms of lead at the end of the synthesis, it's only 45%. So more than half of the lead actually is left in the solution. If you work at lower amounts of lead, you get very bad nanocrystals. And the reason is that lead is partitioned in equilibrium between the nanocrystal phase and the solution phase. So if you try to push all the lead in the solution, then all in the crystal, then the ligands, free ligands, will recall lead from the nanocrystal phase and lead to phosphor ripening, basically. So our idea was, okay, because it's very difficult to introduce ions in the perovskite, other ions than lead, why don't we use a bunch of different ions that basically do not participate in the perovskite structure, but form complexes with olates? So they might push all the lead into the nanocrystal phase. And we actually tried almost all possible cations. And the dates of the synthesis, we don't need to tell them. But basically, at the end of the synthesis, all the lead is in the nanocrystal phase. and what you're left in the solution is metal carboxylates. Okay, so imagine that if you use zinc, for example, or I don't know, aluminum or tin, or calcium or magnesium, which are not so environmentally bad, you end up with these metal olates, which are easier to dispose of than lead olates. And so regardless of what kind of exogenous metal cation you use, you end up always forming beautiful nanocrystals of perovskites containing only perovskites. Now, if you add silver instead, what happens is that silver bromide has a very low solubility. So you nucleate silver bromide, and then because silver bromide has almost no lattice mismatch with the cesium lead bromide, you go to a core shell. So you completely deplete the silver in a matter of few seconds, and on top of them, you grow a cesium lead bromide core shell nanocrystal. Now, under the electron microscope, of course, the silver bromide decomposes to silver because of high beam sensitivity. Actually, silver bromide was used in photographic plates, to converting silver bromide into silver by light. So when you look at these things under TM, you always find out a silver domain into a cavity, which was the space occupied originally by the silver bromide. Now, what you do with this, you can, of course, do halide exchange and go to the cesium lead, corresponding cesium lead chloride with a core of silver bromide or chloride. We don't know exactly because this gets degraded. If you do the same actually with the iodide, it turns out you get a completely hollow structure. So it sucks out the silver bromide or the silver. And the reasons, there are two reasons. One reason is that actually, even if you do it with metallic silver particle, you will dissolve them. Because these iodide ions, they actually even do it with gold. They make a monolayer on the surface of the metal, they raise the Fermi level, and then they increase the propensity of the metals to donate electrons. So if you want to turn a metal into a reducing agent, just react it with iodide. Also, the other reason is that when the iodide diffuses into the nanocrystals and exchanges the shell, and even if it exchanges the core, then it turns into a silver bromide, which has a completely different phase than the shell, so it's highly unstable. Anyway, a long story short is that silver then has a high diffusivity and gets out very easily of the nanocrystals, and you get this hollow structure. So once you get this hollow structure, you can then back exchange to bromide and the chloride, and now you have samples of gigantic hollow cesium lead halide nanocrystals on which you can do optical studies, for example, so you can do how the carrier relax. Lifetime is longer in these nanocrystals, which are relatively big compared to the smaller nanocrystal than one can do with standard colloidal synthesis, and this is probably due to higher sp hybridization in extended metal halide, which partially prohibits the interband transition. We also did a PAM probe experiment as a function of PAM fluence to basically extract the bi-exciton lifetime, and the bi-exciton lifetime in these materials fits very nicely into this curve of bi-exciton lifetime as a function of the nanocrystal volume. So essentially, the hollow region inside doesn't do much. Actually, these nanocrystals have a very good quantum yield. So the additional surface that you form inside does not really play a big role in the optical properties. Now, what do we do out of these nanocrystals in general? So Maksym showed that, so first of all, we can easily do a halide exchange, as I said, and this was shown by our group and Maksym more or less the same day. Yeah? We published 2 papers, one after the other, in a matter of 1 weekend. And this on a small nanocrystal is a very fast process. So you can easily go from one composition to the other in a matter of basically a few seconds, all right? So we said, okay, why don't we study this halide exchange in gigantic nanocrystals? Because gigantic nanocrystals, as Maksym is showing, are starting to catch a lot of interest in the community because of their quantum properties. And so we said, okay, why don't we compare gigantic cubes, 40, 50 nanometers in size, with gigantic hollow cubes to see whether they behave differently and differently from smaller nanocrystals in terms of halide exchange, because we might make heterostructures which are completely new. And so, for example, if you start from cesium lead bromide and you exchange into the chloride, actually you get intermediate samples, for example, which are completely alloyed. This is nothing special, and it completely conforms to the case of smaller crystals. Actually, if you do iodide bromide exchange, now the difference in ionic radii between iodide and bromide is considerably bigger than between bromide and chloride. So you might start seeing a phase segregation effect. And indeed, if you start from cesium lead bromide and you start exchanging iodide with bromide, you start seeing in intermediate cases double peak features, telling us that actually we are forming segregated domain of bromide and iodide in the same nanocrystal. Okay, but actually, if you take one of these aliquots and you wait a few hours, in those few hours the ion keep diffusing, and at the end you end up forming an homogeneous alloy. So there is a time frame of halide diffusion, which is you can measure in the time scale of hours in these materials. All right. So again, not a striking difference between hollow and non-hollow crystals. But now, if you exchange iodide and chloride, you start seeing very interesting thing. Now there is a huge difference in ionic radii between these two halides. So the system really, at intermediate stages of exchange, really tries to make a segregated domain. And now you can see that the system struggles with the strain, because what you're forming is basically you have a sphere inserted in a circle, for example. If you forget about this hollow domain, this is the shape that you can inscribe in a circle, in a sphere inscribing in a cube with the lowest possible interface between the two solids. The other interesting thing, you see that these channels are being formed from the core to the outer surface. If one looks very carefully at these structures here, which are rich in iodide, these are channels drawn in the cesium lead chloride phase, which are rich in iodide. These are basically chunks of all inorganic radlets and Popper phase. So here the octahedral connectivity breaks, and they might represent channels through which halide gets exchanged very quickly from the surface to the core. Now, if you go to complete halide exchange, the strain keeps building up, and most likely the strain gets released through these channels here, where the octahedral connectivity is already broken. So you end up forming this hollow structure at the end, in which there are channels connecting the core, the void region, to the outer region. All right. If you do the same with regular cubes, actually, because you don't have this hollow surface, and I will show you later that this hollow surface actually promotes the formation of these RP channels, in this system doesn't have a very systematic way of releasing the strain. So what the system does at the intermediate stage of exchange, it starts cracking. It basically breaks like a nut. And but for some reason, and it makes a core shell structure, but for some reason, at the end of the full reaction, this surface somehow heals a little bit. This crack rearrange, and basically they coalesce into a hollow region. Okay, so you start from non-hollow particle, you end up into a hollow particle. And you have these intermediate samples, both in the previous case and in this case, where you have core shells. This is probably the first case of a core shell, halide perovskite nanocrystals. Actually, is a very bad case of core shell, because you start from cesium lead iodide, which has a quantum yield of around 40%. You make a core shell which is 20%, because the system is struggling like crazy with strain. If you exchange all the iodide with chloride, you get to almost 0% quantum yield. And also, these things are very short-lived. So if they live only for 3-4 days. So if you want to make a device, you have to use it only for 3 days. Anyway, so a very bad example of core shell, but that's what you get with, that's the reality, all right? So now, if you exchange chloride with iodide, you start from chloride and iodide, then you start seeing all these kind of RP phases forming and actually propagating from the outer surface to the inner surface, or the other way around, if you want to think of it. And so the hollow structure promotes a lot the formation of these RP phases, which form wherever there is a surface, because that is very easy to exchange halides. So either on the outer surface, as you see in these regular cubes, or at the outer surface plus inner surface, you have this formation of these RP faces, which are again channels through which the halide ions get exchanged very quickly. And so you form a sort of double core shells in the case of the hollow cubes, because through these channels, the halide ions can migrate very, very efficiently. All right, so again, these are RP faces. The system struggles to make a core shell. It doesn't want to create this heterostructure. If you force it with a lot of iodide or chloride, it does form it, but the heterostructure is metastable. And whenever it gets the chance, it tries to form this RP phase, because this is the only way for the system to accommodate these two types of ions with very different sizes. Okay, so switching completely gear, because I want to give you also an idea of 3-5 nanocrystals that we have been developing in our group. So first of all, we are also very interested in developing short wavelength infrared light sources for a series of reasons. Cameras exploiting light in this range for acquiring imaging and perform analysis. We are also looking into basically consumer optoelectronics, where the prices really makes a difference. And so you want to develop IR emitters or IR sensors, which are costing maybe just a few cents. And so the idea of using colloidal quantum dots of emitting in the near infrared with a very cheap preparation route is very important. Of course, another interesting application is LiDAR, mainly for automotive. And so this drives the need in this area to really try to make these very cheap light sources. And in this context, indium arsenide quantum dots are a very interesting material. These materials have been synthesized since ages. I was involved in the first generation nanocrystal kind of frenzy fever in the late 90s. And you can see that, already in the end of 80s and beginning of 90s, people were really trying to make indium arsenide nanocrystals, mainly using this very nasty chemical, which is 3-methylcellulosine. The synthesis scheme actually is very simple here. You react 3-methylcellulosine with indium trichloride. This creates this very stable and volatile compound, which is chlorosilane. So basically, also by mass action, it's very easy to drive the reaction towards the formation of indium arsenide. The advantage is that you form arsenic 3-, so it readily coupled with the indium. And already, in the late 90s, people were getting relatively good quality nanocrystals of these materials. They made also first electroluminescent devices. And actually, indium arsenide is not as toxic as you can imagine, because the bond between indium and arsenic is covalent. And it's very difficult to break it in polar media. So if you throw indium arsenide dots in water, you're not going to get arsenic 3+ that easily, okay? Or not as easily as if you throw perovskite in water or cadmium selenide or lead selenide, because it's a covalent system. So that's why, indium arsenide is considered not a very toxic material for consumer electronics. You might argue about, the criticality of indium, for example. Now, but of course, this synthesis is, first of all, this chemical is extremely nasty, and it's very expensive. So unless you have really high-end application, you want to try something different, okay? And the community has been working on, for example, alternative compounds like, for example, amino arsines, which, they also decompose in the reaction environment of a typical hot injection synthesis, but they would free arsenic 3+. So you need a reducing agent. There are many reducing agents. A very popular one is this amino aluminum hydride, okay? And so you basically throw these two things together with indium chloride in in a pot, and you do indium arsenide. Now, the magic ingredient in this kind of synthesis is zinc. Zinc was found by many groups and also by us to lead to very good control on the sides, actually also good PL quantum yield of the resulting core shell nanocrystals, which you make once you finalize the synthesis. You throw them in a mixture of zincolate, for example, and phosphine selenide, and then you can grow a shell as thick as you want. We could grow up to a 7 molar area shell. So you're really encapsulating very stably these nanocrystals into this gigantic shell of zinc selenide. And somehow the zinc selenide at the beginning of the synthesis play a role in getting good starting indium arsenide quantum dot. And I'm going to come back to that in a second. Now, this is a typical TM and add stem and elemental mapping of the indium arsenide nanocrystal. So this is really a gigantic system. It starts really comparing to what you get by self-assembled epitaxial quantum dots, where you basically grow indium arsenide on a substrate and then you completely bury in another material. No? So you do strain analysis and you indeed see that there is a strong variation in the lattice parameter between the core and the shell. Okay. Now, we did a lot of analysis, and it turns out that indium it's also present in the shell. Okay, and especially in the region, in the inner region of the shell surrounding the core. Now, I don't want to go too much into detail of this, but we did a lot of experimental studies using, XPS, XAFs, Xanes, and also developing modeling. And the summary of the story is that actually, when you grow an indium arsenide core in the presence of zinc, and then you soon after you grow a zinc selenide shell, it turns out that you form an intermediate layer, which is indium zinc selenide. And this indium zinc selenide has a lattice parameter between indium arsenide and zinc selenide. So it sort of tries to act as a spring to, let's say, try to ameliorate, to reduce the strain between the core and the shell because, this very large lattice mismatch of 6%. Now, it turns out the story is more complicated because one could imagine that, okay, this is the best synthesis, okay, and we understood that. But for example, what if you, for example, maybe this intermediate layer comes because there is an excess of zinc coming from the synthesis of the core, which we know is not entering the core. We don't find zinc in the core, but somehow it's sitting on the surface. What if we clean it and then we add zinc selenide shelling material and we grow shell? Okay, we do almost the same in terms of PL quantum yield, slightly worse. So also in this case, we are forming an interlayer. So what is going on there? What if we do the synthesis without any zinc at the beginning? If we do the synthesis without any zinc at the beginning and then we just introduce zinc selenide afterwards and we do the shell growth, here the PL quantum yield is very low. So in this case, for some reason, in all these cases, or for example, what if you add then after the synthesis zinc selenide and then you grow shell? Well, you get a little bit of improvement, but nothing compared to this. So you really need zinc from the beginning of the synthesis, and although it doesn't really get into the core, it does something. And so we did a lot of studies, again, a lot of experiments and a lot of modeling, and it turns out that indium arsenide nanocrystals have a high density, especially of hole trap states, okay? And these hole trap states are effectively passivate. I think there is something not showing very well in the presentation, but anyway, so hole trap states, which are mainly localized on the -1 facets of indium arsenide, which are rich in indium, in arsenic, so they expose arsenic dangling bond. Zinc selenide used during the synthesis, partially buried in this facet, basically passivates all these trap states, and then it remains there. And when you grow an outer layer of, an intermediate layer of indium zinc selenide, it passivates much better the crystal than if you just do a post-synthesis treatment of zinc chloride. It does a little bit, help in passivating this whole trap states, but not as well as in this case. So another things that we studied recently was, okay, so a typical synthesis of indium arsenide and nanocrystal use a reducing agent, which was this tertiary amine bound to the aluminum hydride. But this tertiary amine is a very small amine and has a very high volatility. So once you throw this reducing agent into reaction environment, it quickly evaporates and causes a lot of temperature fluctuations, makes the synthesis unreproducible. So what if we replace that short tertiary amine with the long chain tertiary amine, okay, for example, trioctylamine? What happens? Actually, what happens is that, when this decomposes and frees the aluminum hydride, this trioctylamine has very low, let's say, vapor pressure, meaning that you don't have evaporation, you don't have sudden, evaporation of the solvent, so the temperature of the reaction environment remains constant, and this enables to grow nanocrystals that are much bigger. So one issue with growing indium arsenide is that traditional synthesis leads to very small indium arsenide nanocrystals, absorbing and emitting around 800, 900 nanometers. And if you want to go all the way to 1.4, 1.6, 1.7 microns, you have to do multiple injections, and you also have to fight against these capricious reducing agents. On the other hand, with this stable reducing agent, we could make nanocrystals which are, much bigger than the traditional nanocrystals grown by these reducing agents, going all the way to 1.54 microns, and with actually record PL quantum yields for those regions of the spectrum using this, reducing agent strategy. This is not the only reducing agents that you can use. You can use, for example, things like Grignard. Okay, Grignard is a very convenient and cheap reducing agent, high reactivity. When used instead of this aluminum hydride amine adduct in the synthesis, immediately leads to the growth of significantly large nanocrystal cores on which you can easily grow a shell and get actually quite a decent PL quantum yield. So the size distribution gets broader, okay? But if you don't care about size distribution, if you just want a broad, efficient emitter in the near IR with cheap chemicals, so these are the ways to go, all right? So now we also work in collaboration with other groups studying in detail the amino sign synthesis route. So if you want to make the best possible monodisperse indium arsenide nanocrystals, there is no way around. You have to use trimethylsilyl arsine nowadays, okay? So these are just beautiful nanocrystals that you can grow with continuous injection of precursors, keeping the nanocrystal growth in the size focusing regime, and getting just beautiful absorption spectra, which means you have very narrow size distribution. Now, what is the problem with this? This is the best possible synthesis that you can find in the literature, and the authors used dioctylamine somehow as a moderator of the growth of the nanocrystal. It's just an empirical finding. This dioctylamine led to very good size distribution. Now, the problem with this synthesis, if you want to use this nanocrystal for devices, it turns out it's contaminated with a lot of organics. You cannot really clean them very well. And we did a lot of analysis on this nanocrystal. We indeed found that there is a lot of organics that remains even if you wash the material. There is a lot of silicon-containing compounds, probably coming from the reaction of this trimethylsilyl arsine with something that is present in the reaction environment. And it turns out the culprit is this dioctylamine. Because dioctylamine in this synthesis, okay, I will show you in a second, reacts with the carboxylic acid that is used in the synthesis. We also use a carboxylic acid as a surfactant. Now, if you use trioctylamine, so last year was the year of the trioctylamine, so we used it in all possible sources. If you use trioctylamine in the synthesis, actually, you don't get this problem. You still get beautiful nanocrystals, and you don't get any silicon contamination and basically very little, let's say, organic contamination at the end of the reaction. And so the origin of this silicon byproduct in the dioptylamine-based approach is that, let's say, oleic acid, which is used as an additional surfactant in the synthesis, reacts with the secondary amine, makes an amide under those reaction conditions, and frees water. Now, water can do a lot of things. So, for example, it can react with the cellular sign, making the silanol. The silanol, on its turn, can react with the oleic acid, which makes olates and frees additional water, or it can react with the silanol and freeing additional water. And this additional water freed keeps reacting and creating a lot of other organics. So, or even oxidizing the surface of the crystal. So if you avoid this reaction at the very beginning with the use of a tertiary amine, you prevent all this, you still get beautiful size distribution, and you get pure nanocrystals that are much more suitable for optoelectronic devices. Okay, I think that's it. Of course, we collaborate with groups of Francesco Di Stasio at IIT. We use these nanocrystals to make very efficient devices, especially nanocrystals which we grow with amino-arsine or Grignard reagents where, let's say, the cost of production of the nanocrystal is commercially viable, if you want to say. All right, so that's it. That's the end of my talk. And I thank all these people here and you guys for the attention.
Questions from the audience, please. So I will start by asking a question. So for the perovskite nanocrystals, for device application point of view, we've been trying to look for these cold shell structures similar to the second part of the work, where you have a kind of a thin layer actually on the surface, not within the nanocrystal, so that we can protect the perovskite, and at the same time, hopefully, we can take care of the ligands, which can cause the issue for the transport. Can you comment on why it's so difficult to make this?
Well, to make core shells in perovskite is very difficult because, you know, the material itself is very reactive, and if you want to do it with ions, you see that they have a very high mobility. So even if you try to segregate some ions on the surface, over few hours, they will rearrange. And if you try to build too much strain in the perovskite structure, either compressive or tensile strain, perovskite, you will have a transition to another phase. So metal halides have a rich variety of crystal structures. So if you try to compress or compact too much, you will destroy it. It will become something else.
Do you think there's any way to go around it, to really, because we don't necessarily have a thick shell, maybe one layer or two layers?
Well, I think the last talk before lunch has shown a very beautiful examples of coating surface perovskite with ligands or also with different inorganic materials that lead to very high stability. So I think there are already good recipes there.
And then in that case, it's more for photoluminescence.
Right. Yeah.
And maybe hopefully we can develop something in the future for electroluminescence.
Yeah.
Marco, please.
I was interested in your mixed iodide chloride. We have tried to make those mixtures, but it's almost impossible to get chloride into an iodide lattice. Very small levels. You need bromide, you need some contracting co-anion. And so I was surprised that you could make those mixtures and
they're stable 3-4 days. They are stable for 3-4 days.
And then they separate.
then the cesium lead iodide transitions into the yellow phase because it's too much compressed. It doesn't like that. And so you start getting gigantic wires of, yellow cesium lead iodide.
Okay, thank you.
Are there more questions from the audience?
I think coffee breaks is kicking in.
Yes, maybe, yeah. Usually I think you have. Okay, so maybe in that case, please join me to thank the portal again for this very nice talk. Thank you very much. Okay, welcome back after the quick break. So I would like to invite our first speaker for the second afternoon session, Tsutomu Miyasaka from Toin University of Yokohama, who will talk about advanced interface molecular engineering for perovskite solar cells.
Thank you.
You're welcome.
Thank you. Actually, the last three speakers are some common point. We started the perovskite solar cell as an extension of dye sensor solar cell. Michael Gretzer is a start of high efficiency ESSC. Okay. Here. Okay. Well, my point today is actually, let me introduce my daily life. I started with going to my own company, the Pixel Technology, which was established in 2004, spending there 4 hours, and I moved to the university to supervise young researchers. So my daily work is occupied by the company work. This is implementation of a plastic perovskite solar cell module. But in university, I started very basic work, something new, because you know, the copper composition efficiency perovskite almost saturated. I personally am not very much interested in making a tandem cell, because single cell efficiency, small one, already achieved 25 efficiency. But the company making a large module, this module power composition efficiency is still much lower than 20%, maybe 10 to 50%. So company have to make a big effort to reproduce this high composition efficiency with large modules. So this is task. So at university, something new. I will talk about this. Up conversion included photovoltaic cell and also device architecture without using a charge transport layer. So first, let's start talking about. Actually, we started the perovskite experiment in the 2006, reporting the student work in Japan-based electrochemical society, and okay, yeah, this was a USA ECS conference, yeah, and the 2008. This is the first report of all solid-state perovskite solar cell. It's the junction with carbon as a phototransport layer and carbon the conductive polymer composite. But efficiency is so low, less than 1%, because we coat a very, very thin quantum dot-like layer. So it's not capable of harvesting light. This is our start. And the first peer-reviewed paper appeared in 2009, as you know. So in Japan, something very impressive thing is the company named Sekisui Chemicals demonstrated large, the flexible perovskite solar cell module. Yes, in Osaka Kansai Expo. So this is a length of 250 meters long. Yeah, this is a big demonstration. So now so much money Japan's government decided to invest for the mass production of perovskite solar cell. And something special for our country, Japan, is Japan is the world's second producer of iodine, natural iodine. So I very much wish Japan can start the installation of perovskite solar cell, because you know the silicon solar cell, almost all materials we imported from other countries. What about the lithium-ion battery? Lithium is produced in Chile and maybe cobalt in Africa. The wind power and robot, China is super maker. So, but perovskite is very rare in terms of all main materials is produced inside our company. So why don't we start the perovskite industry country? Because of iodine rich country. So actually, perovskite is very strong light emitting materials. So what happened is after we established our companies, so young researchers joined our company who got lecturer in university, supervising Masako student, Kojima. So Masako's student, he wanted to start the photovoltaic research, but he was doing light emitting perovskite, 2D, respecting Professor Michi very much. And when he joined our group, what do you want to start? I think he was interested in the DSSC, but he said, I have some strange materials, it's perovskite. It's capable of luminescent. So he asked to me if he could start these materials. Okay, I said yes, because from my understanding, any kind of photosensitive materials is capable of generating some small response. So he started this one, taking 3 years, then achieved the power conversion efficiency exceeding 2%. This is a story. Now the perovskites also can be coated at a low temperature on plastic film, ITO plastic film, and then our company commercialized the special inkjet printing machine to coat the perovskite on glass and plastic. And just last year, we achieved the power conversion efficiency 18% for plastic perovskite solar cell made by inkjet printing system. So first topic is for perovskite solar cell, the photocurrent density is not special. The quantum conversion efficiency almost unity, 100%. This is common for the DSSC. What is very unique is the relatively high voltage output from the band gap, thanks to that defect tolerance nature. So we like to sustain this high voltage without loss of degradation by doing some passivation of the interface. So the interface is here, and it can absorb the moisture from the ambient air. Also, the junction here is not very good. Generally, in organic solar cell, they are making epitaxial connection, the junction interface, but it's just physical connection. So we like to modify this interface by, for example, using organic molecule to change the surface potential or intensify the rectification of selective charge transfer. And I'm particularly interested in inserting some hydrophobic molecular layer to block the invasion of the water moisture. So to enhance efficiency, we need to make a large grain with flat surface, and by minimizing the grain boundary area. So, but still, the grain boundary is rich of defect. So now popular work is to passivate this grain boundary by using variety of molecule. Yeah. Generally having a molecule bearing a amino group. And it's just, this PBABR is very popular materials, but we chose this one. This is a cyanogen derivatives. The cyanogen derivative can coordinate the lead to passivate the iodine-free place. So this is an example of cesium lead, the mixed halide case. So this TDCA can passivate this defect, and the result is it can shift up, change the energy level. So the gain is increase in VOC on the one side, but the indoor, this VOC enhancing effect is still work in indoor. Generally, the indoor photon flux is 1,000 or 2,000 that of outdoor. So if we got the 1 milliampere, the same module, this one just generate 1 microampere indoor. Generally, we have a loss in the voltage, but fortunately, we could reproduce enhancement of photovoltaics by this method. So if we could enhance efficiency, the immediate application is IoT. And also we could find the ideality factor also improved by this participation. And when we use a wide bandgap absorber, this is a iodine bromide 50-50 mixture. This is a bromide rich one. The band gap is almost 2 eV. So we could get a high voltage exceeding 1.5 volt, almost the same comparable as alkaline batteries voltage. So we have been focusing on the technology to enhance the VOC. And our champion data is we got a VOC is 1.2 from the absorber having the band gap of 1.5. This is FA lead iodine mixed halide. It's almost that the VOC loss is comparable with that obtained by gallium arsenide. So this shows we modified the interface between perovskite and ITO with hot transport materials. This is very hydrophobic, like this. And this is a new material synthesized, and it's a donor-acceptor combination in this one molecule. So when we use this one, so durability of the life of the device is drastically improved. This is very important because the one drawback of perovskite solar is high cost. The perovskite semiconductor is very, very cheap. That material cost is roughly just $1 per square meter. Silicon is 10 times more. But we have to use the conductive transfer electrode, ITO, FTO, and also ionic crystalline perovskite is very weak against moisture. So we have to combine this one with so-called gas barrier materials, gas barrier film. This gas barrier film manufactured in many companies, but generally price is generally more than $30 per square meter. Very, very costly. For example, a gas barrier ability that's 10 to the -5 gram water per square meter that can work, but this cost is high. But by combining this kind of interlayer, then we can use a less expensive gas barrier film to reduce the total cost. This is a PIN device using a nickel oxide. The surface is participated by SAM, new SAM. The SAM materials are actually synthesized by our collaborator, and it has a carbonyl group. This can coordinate to the lead cation. So that we can have our oriented monolayer here to do the selective acceptance of hole here. Then you can see the interface between perovskite and ITO. The commercial, this is a patent. we could observe separation of the layer here. But by using this one, we can continue structure almost seamless junction. By using this one, we can also enhance the durability. Like this. Yes. Okay. The next topic is Maksym. I got a postdoc working with Maksym, and what the property of Maksym is electroconductive, and it's physically, mechanically stable, and we can modify the surface chemically, and this is hydrophilic. Hydrophilic, that means that we can make a good contact with the surface of perovskite. But there are some weak point of Maksym. The Maksym is a titanium carbide. The titanium can be oxidized under exposure to water and moisture and oxygen. Okay. So after oxidation, surface of Maksym is covered with hydroxyl group, TiOH. That leads to the degradation. So we like to reduce this hydroxyl group. So we found some effect by using a boron. Boron coordination to the surface. If we use the Maksym with a nickel oxide, we could get an efficiency exceeding 26%, and as you see, life is good. But if the same cell is exposed to high humidity ambient air, the degradation starts. Okay. So generally, the Maksym has been used as a component of whole transport materials as an additive. I don't think anyone have tried to use the Maksym as a single whole transport materials. This is unpublished data. We're tackling to use the Maksym as a standalone single whole transport materials in inverted PI in the cell without using nickel oxide. The technology is to improve the surface by reacting this sodium boronate to intercalate boron, the surface of Maksym. By using this, we can detect the reduction of hydroxyl group on the surface. So by this technology, we could get a very robust Maksym-based PIN device, and device can be fabricated under air at high humidity ambient air fabrication. And also the unencapsulated device exposed to the high humidity ambient air like this, it is working good. This work is now still being continued. We have to enhance more the stability of this Maksym-based perovskite solar cell. So like this, some material can be useful to enhance improve the interfacial structure composition. So next is one of the topics I like to show that's just published after rejection by many journals. Okay. Now we say a whole transport layer is replaced by SAM. It's very popular technology. But still we have to use ETL. If the ETL is replaced with SAM, we have still used HTL. But that charge transport materials has their own stability, and nickel oxide is not perfectly stable. And iodine migration also invade the charge transport materials to degrade. The other problem is high cost. I I joined some international conference in China, and they gave us the visit of a big company like GCL. So in my personal discussion with GCL people, they don't like to make the general PIN device. Why? They hate to use a fluorine, high cost. This is a big problem. So we are thinking to replace all transport layer by SAM. But this is a very popular material, two parts. Here, this one, the dipole moment, by orienting the molecule, we have generate a local field to selectively accept hole and reject an electron. This is the idea. But now, our challenge is to replace all transport layer with SAM. This is the imaginary view. So actually, it's not easy to coat the surface of the top of the perovskite with SAM. If we coat the SAM solution on the top of the perovskite, the surface perovskite can be dissolved. So, but and also commercially available materials are limited. We chose this one, carboxyl group bearing the fluorine as an N-type SAM, electron selective. And what we have done is we made a half unit cell like this. This is the P-type SAM modified half cell. This is the N-type SAM modified half cell. These are jointed and they treated at high mechanical pressure, taking 1 hour, temperature 60. So Professor David Cahen indicated, so lattice is dynamic. So it can, inside is a diffusion of iodine. So we could make two unit cell to unify to be a continuous one crystalline layer. It's seamless. This is by fusion, crystalline fusion technology. It was not so difficult, thanks to the perovskite property. So we could make the all SAM based device, and then we try to change absorber, MAPI and FAPBI3 and mixer. Unfortunately, the fill factor was low. The internal resistance is high. So we could not get a high efficiency, but this is, I think, the first demonstration of all SAM device. Because of low efficiency, paper was rejected. Finally, we had a home at the chemical science paper. Okay, it's a perfectly bifacial, And because of the without transport layer, the durability is not affected by the charge transport materials. So the durability is relatively good. And, so the postdoc working this one, so he's Dr. Amamiya, he created this illustration. The guy is combining holes. The lady is bringing electrons. This is the perovskite, I think. This is a nice illustration. We hope to be, it's in a front cover, but it went to the back cover. Okay, this is the up conversion. So why up conversion? Because if we utilize the IR light, the thin perovskite can work under IR light. But because of very narrow band gap, the photovoltaics is very small. But if we could up convert the IR to visible light, we can utilize IR light to generate still high VOC comparable to the visible sensitive device. The method is like this. We use IR absorbing organic dye. Why? The up conversion materials is optical absorption coefficient is very low, but dye is very strong absorber. Then IR light absorber dye and the excitation energy is transferred to neodymium and erbium. This is a metal composite. So this materials is already published several years by my collaborator. The one of the typical up-converting materials. So inside the one, so accepted IR energy is converted to erbium complex, and up conversion taken here by two-photon process, two photons. So electron is pumped up to the f orbitals, and finally the energy can activate a perovskite absorber here. This is I show here the green light, but not actually green light emitted. This is a Dexter type element, the contact. The excitation energy is transferred. Okay. So this is some video. Now this powder, okay, upconversion perovskite powder is irradiated with IR light, and we can see the green light emission. So dye is absorbing, dye is absorbing this wavelength area and emission here. Still other system is very poor. Emission is a band-like. But anyway, this is the start of our challenge. And these are published. And what we have done is we make a coaxial materials incorporated with this metal-metal complex. And this was the spurted inside the perovskite cesium lead iodide layer. Then shining light, we could detect the response of IR response like this, but very small. And actually we could increase the photocurrent density. So the gain is relatively high voltage, 1.2 volt, can be produced by visible light plus IR light. Okay, finally, I'd like to touch about, say, manufacturing of perovskite cell. Our student is making this kind of module, plastic module. I always bringing this one. Yeah. These were made by students. Okay, no problem. Okay. So what is necessary is a conductive plastic, the ITO plastic, is commercializing for sale from my own company, Pexel Technology. This is some special technology. We are using almost amorphous ITO layer to reinforce the contact between ITO and PET film surface. Not 100% amorphous, but amorphous crystalline mixture. So the late controlling process is laser patterning to make a 3D structure. And in future, maybe Sexy Chemicals is doing this one, the roll-to-roll process to coat perovskite layer and other charge transport layer. But this is a rate control process using a laser describing. Okay. So last year we did an instrument of the plastic module at the Yokohama Bay. And wood deck of Yokohama Bay is covered with our plastic perovskite solar cell. And this one, in a Thai, actually in Japan, due to the construction rule, we cannot put a solar cell on the wall of a house. But Thai, it was possible. So we decided to install our module, the southeast, west, and north side with perovskite module to test the durability. Okay, the summary. So to summarize, VOC enhancement is a key technology to further improve perovskite photovoltaic cell. And we made a charge transporter free all-sum device. Although the efficiency is very low, but we could demonstrate the performance of cell for variety of the perovskite absorber. And boronized Maksym is a new materials. It shows a very high moisture resistance and high durability. So from now we can use this one as a standalone hot transfer materials. And up conversion can harvest IR light and convert this IR light energy to high voltage output exceeding 1 volt. But it needs a fundamental improvement to the energy transfer system. The energy transfer efficiency is still low. It's very high difficulty work. So in Japan, the perovskite industry is increasingly focusing on lightweight flexible module. Thank you for your listening. This is my another field of work. I have been publishing paper and violin journal, and my fourth article is just published in March last month. I discovered this double bass made by violin makers, very renowned violin maker. So publisher introduced myself here. He studied craftsmanship to Torino-based violin makers, and he's known as the inventor of perovskite. And actually, 2 days ago, I just finished my performance in April 26th. I finished this performance and rushed to the airport with my wife together and take a midnight drive. I was maybe thinking to cancel this performance. This is coming twice every year. So this is my another award. Thank you.
Maybe next time we can also invite you for concert.
The questions.
In the case of modules, the metal is maybe getting into contact with the perovskite. Is that not a problem? Because the metal is going from the back to the front.
Yeah. We have to replace. We are now trying to replace with carbon-based materials. Okay. There is no many choice. Carbon or gold is too expensive.
I think your boronized Maksym was not highly conductive enough because it was supported on ITO. Can you remove the ITO and just use the Maksym?
Yeah, we have to try that one. Now it's not easy. The ITO itself is high costly. We are now trying to make a competitive ITO and metal to reduce the cost. But Maksym itself is also sufficiently conductive.
The up conversion has been on my mind for a long time, but the issue is that the conversion efficiency depends on the square of the light intensity. And so unless you go to 1000 suns, you will get a poor efficiency.
Yeah, this is
the penalty.
Great question. So it can work under laser, but solar intensity is difficult. So we have to increase the lifetime of triple state. So it's a there is big difficulty. Well,
Thanks for the very interesting talk. A quick question about you use the unique structure with N-type and P-type cell, and then laminate to form the device. However, the target is to increase the stability. However, try to use like different metal oxides as a transport layer, different type of metal oxide as a transport layer, and then maybe also increase stability. However, compare or think about.
Yeah, this is P-type, N-type metal oxide semiconductor. If it can work under low temperature. Yeah, this is an alternative way. But because I'm a chemist, I'm interested in make interfacial monolayer.
In one of your first slides, you use, I forgot the name of the material, TBP something, to replace spiral emitter. In that case, you would that material doped or undoped?
Undoped.
Undoped.
Undoped, yes.
Okay. The connectivity is very good.
Dopant free, yeah. Okay. It's very necessary. Dopant can diffuse. So.
Sure.
Thank you very much for the presentation, Professor. Actually, I was thinking about the usage of down conversion material in the perovskite. So instead of up conversion, because it have a low quantum yield, down conversion have the high quantum yield. Also, when it absorbs deep UV that is less than 300 nanometer, it is useful for the purpose of reducing the perovskite degradation as well as for the increasing the current density.
Yeah, thank you for the advice. Yeah, that's right. Well, in the solar spectrum, IR light is richer than the UV short wave light. So, but we can combine these two technologies. Thank you.
Thank you.
Is there any last question? If you like to take this opportunity. Yes, then we take the last question from here.
Thank you. Thank you for the speech, and also I would like to talk about the SEM N-type and P-type device, because in this type of device we are sacrificing the HDL and NDTL for stability. But do you have any idea on how to improve then the efficiency of this type of device if we want to have this feasible and actually in use, since it will be so stable?
Yes, actually, recently people said some cell is not very stable against reverse bias application. So to stabilize that interface, maybe we have to insert another layer. I'm not interested in kind of top construction. It's some very thin insulator layer, but accept that tunneling of carrier. This kind of layer is combined with some. This is one idea.
Thank you. Yeah, with that, please join me thank Tom again for his very nice talk. I would like to introduce our next speaker, Nanjing Park from Tsutomu University, who will talk about the discovery and the evaluation of perovskite solar cells. Welcome.
Thank you. And first of all, I'd like to thank the organizers, the Wang, Tae-Woo, and Ellen, also the Professor Inganas. Well, I'd like to talk about discovery of the perovskite solar cell and their technological evolution. Well, here is the shown here is the first solid-state perovskite solar cell that we reported back in 2012 August, As you know, the methyl ammonium lead halide perovskite was first synthesized in aqueous solution by the Weber, Dr. Weber, in Stuttgart University back in 1978. And then almost 31 years later, Professor Tsutomu Miyasaka reported for the first time the perovskite sensitized solar cell. That means the perovskite is attached on the titanium oxide surface, and then still it has the liquid electrolyte in dye-sensitized solar cell. The problem is that the perovskite is quite quickly dissolved in polar liquid electrolyte. So this material may not be useful for the electrolyte containing solar cell structure. So to solve this issue, we introduced molecular whole transporting materials called the spiral compound, and then the efficiency was almost 10%, and then we show the 500-hour stability without encapsulation. And also the methyl ammonium lead iodide solution, precursor solution, was prepared in the gamma butyrolactone. At that time, we did not use the DMF DMSO. Also, gamma butyrolactone is kind of the polar protic solvent. And then the important point is that we increased the concentration of the precursor solution, which is very important to reproducibly form the perovskite materials. Also, to find out the suitable solid whole transport material, we investigated a lot of the whole conducting materials, and by considering the HOMO level is very important to transfer the holes from the perovskite to the whole conducting materials. First, we try to we pick the P3HT as whole transporting material, but the first the attempt was unsuccessful. Its efficiency was pretty much low, as low as 3.3%. And then the current density is pretty much low, and then the fill factor is very awful. This is because the polymeric geometric nature. So this material is difficult to infiltrate into mesoporous titanium oxide. First, we use the mesoporous titanium oxide as scaffold layer. And then to solve this issue, we switch the whole polymeric material by the molecular type whole conducting material called the spiromutate. And then the efficiency was around 6%, with titanium oxide thickness 1.3 micrometer. To improve further the efficiency, we increased the thickness 1.8 micrometer, but efficiency could not be improved. So this is because in our previous work, actually 2011, we reported still the improved efficiency in dye-sensitized solar cell structure. At that time, we measured and then estimated absorption coefficient of the methyl ammonium iodide, which is 1 or 2 orders of magnitude higher than the conventional N719 dye, which is commonly used for dye-sensitized solar cell. And then based on the Beer-Lambert law, simple this equation, the absorption thickness is inversely proportional to the absorption coefficient. Therefore, if you have the high absorption coefficient, you don't have to increase the film thickness. So instead of that, we decrease the film thickness from the 2 micrometer to 1 micrometer. We observed the continuous increase in power conversion efficiency. That is because of the improved fill factor and also the open circuit voltage. And then we further decreased the efficiency up to 0.6 micrometer to decrease the efficiency. We decreased the titanium oxide film thickness up to the 600 nanometer, and then gradual increase of the power conversion efficiency was achieved, which is due to the gradual increase in open circuit voltage and fill factor. And then we proved that even at 0.6 micrometer, there is no change in short circuit photocurrent density. And then this work was reported in 2012, August. And then this is actually the first report on stable, high efficiency solid state perovskite solar cell. And then summarizing here is the seen by the some contribution of the publication. As you know, 2009, Tsutomu Miyasaka group published one paper showing 3.8% efficiency in the liquid junction solar cell. And then there was no paper next year, and we published also the improved efficiency using the liquid type sensitized perovskite solar cell. Those are the from the 2009 until 2011. Why only 2 papers came out? This is because of the stability issue, the quick dissolution of the perovskite in the liquid electrolyte. So after discovery of after report on the solid state perovskite solar cell, and then the publication increases exponentially up to 2018, and then even after that, gradual increase in the publication, and then we had last year we had almost 7,000 publications came out. And then after the report of the solid state perovskite solar cell, and I was asked by the Professor Prashant Kamat, who was the editor-in-chief of the Journal of Physical Chemistry letter. And then he asked me to write the perspective of the perovskite solar cell. And then at that time, my title, as you see here, I expected 20% efficiency, but my early prediction was completely incorrect. And then now we have the 27.3% efficiency from the single junction, and then which is even higher than the single crystal silicon solar cell. And then the 2 main the factors contributed to increase the efficiency of the perovskite solar cell. One is the adduct method, and the adduct is, as you know, the adduct is when you when you react Lewis acid with Lewis base, then you can have the adduct, and the formation of adduct can be explained by the molecular orbital theory. And in our precursor solution, we have precursor material like the methyl ammonium iodide and the lead iodide, which is dissolved in DMF, polar solvent. In that case, we also include the DMSO. DMSO is well-known Lewis base, and the PbI2 is well-known Lewis acid. Therefore, there is chance to make the adduct. So, taking advantage of this kind of adduct, then we selectively remove the DMF solvent to make the adduct using the anti-solvent method like diethyl is. And then the adduct is adduct intermediate is can save the time, retard the crystallization, so that you can have the high quality of perovskite. Except for MAPBI3, FAPBI3, you can make this kind of using the adduct method. And also, the composition is very important. We started with methyl ammonium lead iodide, which is about 1.65 eV as band gap energy. And then if you change the A site cation from ammonium, then you can either also decrease the band gap energy up to the 1.47 eV, and then you can utilize further the incoming light up to 840 nanometer. However, the alpha phase, the FAPBI3 is stabilized at high temperature, but at room temperature, delta phase is tends to be stabilized. So, in order to stabilize the alpha phase FAPBI3, we need a certain amount of the smaller size cation like the cesium. If you include the 10 molar percent cesium in A site, then even at room temperature, you can stabilize the FAPBI3 alpha phase. So the cesium is kind of the stabilized for alpha phase FAPBI3. And then, but what governs efficiency, stability, and scalability of the perovskite? The question, to answer the question, is it the bulk material only important? Then in part, yes, because as I mentioned that we can improve the crystallinity using adduct method, and then the composition optimization can improve the efficiency. However, stability and scalability issues still persist. Then the performance, including stability, not only the performance efficiency, including stability, is not only bulk limited. And then probably critical process occurs at interfaces. That means interfaces becomes more and more important. And then when you take a look at the evolution of device structure, first we use the mesoscopic adsorbed structure, and then the mesoscopic field structure. We have a lot of the perovskite layers, and then just NIP structure. This is called the normal planar structure. And then recently the people are focused on the inverted structure, PIN structure. And then the inverted structure is better in terms of the stability compared to normal planar structure. However, it was a low efficiency, so people would like to struggle to improve the efficiency using the PIN structure because of better stability. So this evolution is not just a structural evolution. This is increasingly shift control from the bulk to interface. And then how to improve the efficiency? Then use in the inverted perovskite solar cell. Then first we deposit the whole transport layer. In that case, we have to manage the buried interface. And then this system, you probably deposit the perovskite. In that case, phase fuel and defectless perovskite film is important. And then on the surface of the perovskite, you need the surface defect passivation because the surface is pretty much defect. And then after that, also you have to control the electron transport layer and its interfaces. For instance, the first, the buried interface, recently we use the self-assembled molecule that is composed of the carbazole moiety, and the carbazole is a little bit hydrophobic nature, so it inhibits the spread of the polar perovskite ink. Then to solve this issue, we introduced some the carboxylic acid moiety, some chemicals. In that case, the Na compound shows pretty much better the surface and homogeneous coverage. And also this the buried interface engineering also can control the interfacial strain. And then we achieved 26.5% efficiency, and at the same time the stability was improved. So interface is very important, not only for the improving efficiency, but also for the improving stability. And then next step, we need some high quality base pure perovskite film, and also defectless perovskite film. In that case, as I mentioned, that alpha phase FFPVI3, we need this kind of phase. But at room temperature, delta phase, the alpha phase tend to be transferred. It's transit to the delta phase. The alpha phase is cubic structure, and there is the bunch of the cube octahedral geometry space. Then the Fa cation is pretty much disordered. So this alpha phase is entropy stabilized phase. However, the delta phase is the phase sharing octahedral, and then the space is anisotropic and the confined cavity. Therefore, the Fa ion is rather ordered structure. So the delta phase is the enthalpy stabilized phase. In that case, the problem is metastable FAPVI3 tends to transfer to the stable FA, tends to convert from the alpha phase to delta phase. Therefore, the energy barrier is, because energy barrier is smaller. So we have to increase the energy barrier. This is a kinetic term. Therefore, to increase the energy barrier, probably we need enhancing the FA disorder. And also, if we increase the PVI bond strength, then probably we further decrease the enthalpy. Therefore, the total barrier may be increased. Then kinetically, we can control the phase transition. And then we have a bunch of the hydrogen bonding in the cuboctahedral cavity of the cubic alpha phase FAPBI3. Then probably we can control the hydrogen bonding. Then we can even increase the entropy of the Fa cation. So in that case, we used a certain the specific the additive here, the pyridine piperazine hydrochloride system, and then depending on the some position of the the nitrogen atom. So the using this the additive first we simulated, and then we found that alpha to delta energy barrier is pretty much increased and then maximized at the 3 PMPCL the additive. And then to confirm the disorder, the improved disorder, we measure the deuterium solid state NMR, which is very sensitive to the some cation dynamics. In that case, we found that the 3 PMPCL, the narrow the peak the width, which means that the Fa cations undergo faster and lesser constrained reorientation motion. That means this order degree of disorder is improved by the 3 PMPCL. And also the aged sample, we measure the synchrotron radiation to understand the lead iodide bond distance change, and compared to control, it's a large change in the bond distance. The 3 PMPCL is relatively the little change in PBI bond distance. And also the violet effect is disorder of octahedral of the PBI6 is less tuned. So this work actually is the open circuit voltage field factor is very close to the theoretical values. And also the PIN junction, the perovskite layer is quite thicker than the NIP structure, which is almost 1 micrometer, 1,000 nanometer thickness. In that case, as I mentioned, that the precursor solution, not the single Fa cation, a mixture of Fa and CS is a certain amount of CS is required to stabilize the alpha phase, as I mentioned. In that case, the cesium reaches bottom and the Fa reaches the top because the difference in activation energy. Usually the Fa is faster precipitation compared to Fa because of the non-hydrogen bonding nature. And to solve this kind of the cation inhomogeneity, so we introduced some specific chemical like the PSP additive in the precursor solution, and then eventually the cation distribution is the homogenized. That can be explained by the some we tuned some the gap between the FA-PBI3 and the CS-PBI3, the activation energy. And then the role of the PSP additive, usually the additive role is that, for instance, we calculated the PSP and then the charge also distribution. And then we found that the space dimension of this PSP is quite similar to the IPBI bond length in the solution. But actually the PSP, we used this additive is quite small amount, 1 molar percent, less than 1 molar percent. That means the additive not directly interact with the PBI2 in solution. Probably the PBI some cluster or the nuclei, and this nuclei it will be controlled by the additive. So the additive is modify the nucleation and the growth pathway. And then after the deposition of the perovskite, then the surface, you have to control the surface. Surface is pretty much defective. Then the conventional method is usually the certain passivation material which is dissolved in isopropyl alcohol. But in that case, we do not have any the optimal surface passivation. So we introduce very small amount of tiny amount of the polar aperitic solvent. Shown here is the polar aperitic solvent. Small amount is very important because if you use the large amount of the polar polysolvent, then you probably destroy all of the perovskite layer. So 1 to 20 the volume percent, 200 volume percent is we found this is optimal some ratio, and then only surface is dissolved, and then using the in situ PL, the spinning stage and annealing stage, we found that conventional the IPA system compared to conventional IPA system, some small amount of the polar polysolvent, N stands for kind of NMP. IPA N system shows the some different kind of the appearance of the alpha phase compared to conventional method. That means the formation of the surface alpha phase is a different way, and also the annealing system, the surface is highly our method shows the highest the intensity PL intensity higher, pretty much higher than the conventional method. That means the surface is quite patch-baited, more patch-baited than the conventional method. And also, if you have the some large defect on the surface, then probably the electron density in near surface conduction band may be low. For instance, control is pretty much low, and then our method show the 4 orders of magnitude higher than the control the electron density, which is actually calculated by the non-degenerated Boltzmann approximation. And then after deposition and then the surface treatment of the perovskite, you need the PCBM, the ETL layer. In that case, one point is that the PCBM is good material, but however, the carbon-60 or PCBM undergoes some dimerization under the light illumination or this thermal stressor. Once you have this kind of dimerization, then you lose some kind of charge carrier mobility of the PCBM. So to solve this kind of issue, we designed the FABA some special the compound which is included in the PCBM ink, and then this material actually control the. Here is the the functional group of the PCBM. This material interact via the pi-pi staking and the hydrogen bonding. That this actually the lock some inhibit the dimerization. So by this the method we achieve the quite high efficiency. And then summarizingly, we need the step-by-step barrier interface engineering is required for control the strain and energetics, and also the bulk perovskite is required some page fewer, and then also the defect less the composition, and also the surface of the perovskite should be engineered to increase the electron density near conduction band. And also the ETL is important for improve the chemical stability in the specific PCBM case. And then based upon this the sequence design, then we saw that this is two interlayers, important two interlayers. Then if we introduce some the semiconducting polarity, for instance, N-type in between ETL and perovskite, and P-type between the perovskite and HTL, maybe so this composite, this design may improve the further efficiency and stability. So polarity selectivity, actually we formed the in situ the formation of the 1D organic leather triangle interlace. We form this kind of the one-dimensional APBIC. This is not perovskite, okay? And then the cation A is MTIM is including some the self element, and then we prepare the single crystal MTIM PBI3, and then using this single crystal we analyze the crystal structure, and then local structure actually is the phase edge sharing octahedral, and the other the cation B is containing the some nitrogen. In that case, the molecular structure is similar. is almost the same, except for only the element sulfur and nitrogen. And then we also prepare the single crystal MAIM PBI3, and then the analyzed crystal structure and found that octahedral in this one-dimensional structure is phase sharing. So without doping, the local structural connectivity can change the Fermi's level. This is not actually Fermi's level. This changes the valence band. For instance, the MTIM PBI3 is HE and the phase sharing structure. The PBI bond is stronger than this one. Therefore, the valence band is upward shift. That means the close to the Fermi energy level. This kind of looks like the P-type nature. And the MAIM PBI3 one-dimensional structure, we found that the PBI bond distance is weaker than the MTIM PBI3 case because of the phase sharing structure. So then this PBI bond distance strength is weakened. Therefore, the conduction band is deeper. Therefore, meaning that the Fermi energy level is looks like close to conduction band. This is kind of the non-doping strategy. It's a pseudo semiconducting type conversion. So using this one, for instance, we inserted a P-type one-dimensional interlayer in between HTL, FA, PBI3, or the N-type into ETL and PBI3. Then, as you see here, its performance is increased. So based upon this information, if you insert the P-type into the HTL, FA, PBI3, and here is I'm sorry, this is N-type. Upper is ETL and FA, PBI3. Then we improved a lot. This is called dual interface semiconducting selective method. So we achieved the 27.6% efficiency. And then the stability scalability is important for industrialization. And then actually I was asked by the company then. So very simple processing is effective for commercialization. And then they do not want to use the methyl ammonium chloride because residual chloride it's hurt stability, and also anti-solvent method is quite it's not good for the some upscaling technology. And also they want to make the some air processable fabrication. And also the stability, as I mentioned, that the interface carbon stability is very important. So, for instance, the moisture stability of the perovskite material, we discovered that the moisture stability is dependent on the facet, crystal facet. And here we prepared some facet enhanced perovskite film, showing that the 100 facet and the 111 facet, and then those film was exposed to the humidity, 40% relative humidity for 200 hours, and then eventually found that the 100 crystal facet is completely degraded, and then back to the delta phase. However, 111 phase is pretty much stabilized. So based upon this information, we prepare the over 98% the 111 phase dominated perovskite film, then show the humidity stability. Also, for air processable fabrication, very important point is that the iodide oxidation. When iodide meet with the oxygen, then the iodide would like to be oxidized. So then in air. So we used some the hydrophobic nature, the additive like the imidazolium iodide, the liquid, the imidazolium iodide, the additive like the BMIT. So the and also the when you prepare the precursor solution, and then probably there is a rapid nucleation happens in that case, the BMIM, the T means the TFA anion, and then the additive actually protect the suppress the nucleation by inhibiting some interaction between the Fa plus and the PbI3 anion. So using this kind of the additive engineering, we effectively inhibit iodide oxidation, and then make the at a different kind of the we increase the relative humidity, but efficiency is almost unchanged. And then at the same time, this air process of perovskite solar cell show the pretty much improved stability. So this is actually the for upscaling. This is kind of the debug coating and the room temperature. We also tested the rigid substrate and also flexible substrate, and there is some specific input here, and we they dropped some 2 points on the debug, and then this is a real speed, and then back there is kind of the air knife here. And then we at the room temperature we can make the perovskite here. So yeah, this is actually a very important process. We do not use any kind of MA shell. We did not use any the anti-solvent process. And then even this is the MA PbI3 case. First we make the MA PbI3 crystals, and then this crystal is put in the closed vessel, and there the MA solution. And the MA solution, there is some MA gas out from the MA solution and go into the crystal. And you can see here the crystal is gradually dissolved and then make the very viscous solution. This is a very interesting phenomena. And then the methylamine molecule is adsorbed, physically adsorbed on the surface of the crystals, perovskite crystal. And then this is a kind of the liquefied because of the methylamine distance is closer. And then eventually it's dissolved. This is actually the viscous perovskite material, and we diluted this the viscous perovskite solution using the acetonitrile. And then we found that this crystallinity, the very large area we coated, and then even from the 1 to 16, there is not big difference in the photovoltaic performance, and also crystallinity is pretty much the same regardless of the position. So that we have to use this kind of method to prepare the Fa PbI3. Unfortunately, Fi cannot be the volatile, therefore it is very difficult. And finally, for upscaling, we need the precursor material, inexpensive but high quality perovskite material. In that case, people are using for Fa PbI3 case, people prepare the single crystal, or alpha phase Fa PbI3, but we prepare the delta phase Fa PbI3 in aqueous solution, which can be used for the precursor material. And then using this material, we actually show that the impurity, for instance, calcium, sodium, or potassium impurity is very important. So, for instance, we need always the high purity PbI2 from the TCI chemical, something like that. And then because the low quality always gives you a very poor efficiency. So very lower the impurity we can achieve by using our technology. And then we achieve the over 25% efficiency. So with that, let me summarize my talk. Well, the solid state, the Perovskite, SOLID, established the foundation of the modern the Perovskite photovoltaics. And then efficiency progress is not only the solution. The performance, including stability, is not only bulk limited. So we have to focus on the interface more and more. So the interface defines performance now, and the stability is an interfacial phenomenon. And also, I like to suggest that the efficient, stable perovskite using MACL-free and anti-solvent-free process is required for the commercialization or upscaling. And also, the universal interface design rules are required, and better understanding of the chemistry and reactive interface also we have to study. With that, thank you very much for your kind listening, and then also my members and the collaborators and the funding agents. Thank you.
Questions from the audience, please. Now I will start with a quick question. So as you show in one of your earlier slides, so now previously the field was dominated by this PI, the normal structure. Now the field is dominated by this inverted structure, and you are one of the few groups which are still working on both structures. And in your opinion, can you comment what the advantages and disadvantages of these two structures? And also, Tom previously mentioned the company in China, they didn't really like the electron transport layer on the top. So yes, can you comment for the future?
Yeah, actually, for NIP structure still is important structure, but because we could not so far find the replacement of thermally unstable the spiral compound. So if we have found some kind of so we are working on the some inorganic layer. Instead of using the spiral compound, then probably this is a useful structure for NIP structure. But so far we could not find this better material. And also interestingly, the MA-PBI3 case is always the lower performance than FA-PBI3. So now FA-PBI3 is well established in the PIN structure. So our laboratory is almost 100% focused on has been focusing on the PIN structure.
Yeah, thank you very much for this comment. And some of our group members might be feeling very, very encouraging because we have spent a lot of efforts trying to improve the thermal stability of a spiral. Okay, any more questions from the audience? Please.
Thank you very much for this nice presentation, and a little bit thank you for the history as well. So I wasn't clear. Did you say in 2012 that you removed the titanium dioxide, or was that happening later? I don't know the history exactly, because up to then it was like a dye-sensitized solar cell, and then at some point not have, because you don't have any titanium dioxide there.
Yeah, first we use the titanium oxide. This is kind of we still use the in dye sensor solar. We still use the titanium oxide, and also the Tsutomu Miyasaka also used the titanium oxide. And then the second, our liquid type perovskite solar cell also used the titanium oxide.
This you told. I mean, I kind of missed when was the titanium dioxide?
So titanium dioxide is actually removed at least we use the tin oxide thin layer. Then we do not use the titanium oxide. Actually, even the normal structure, we still use the titanium oxide. But in this normal structure, the tin oxide is better than the TiO2. So we use the tin oxide. And after that, this is probably the Jinpu in China. He applied the amorphous like the tin oxide in the normal the NIP structure, and then which showed the better efficiency than the TiO2. So people switched to the tin oxide, and at that time they do not use the TiO2.
Okay.
Yeah.
So,
I take the last question from you.
I just wanted to comment. And actually, last year we published a paper with the Italian colleagues, and it was a mesoscopic TiO2. NIP structure, 5,000 hours stability at 85 degrees under illumination. Nature energy. We had replaced this spiral by arylamine, but Frank tells me he has stabilized the spiral, so we will go back to spiral. Just for clarification. There has been an evolution, but the boundaries are not well defined.
As part of the history, I was.
Yeah.
Yeah, with that, I think we please join me second for this great talk. Thank you very much.
Thank you.